Hello there, and welcome to Science for Sleep, where curiosity slows down just enough to let your thoughts settle, and science takes its time, gently unfolding one idea after another. Tonight's quiet journey drifts far beyond anything we can touch or visit, into regions of the universe so vast and unusual that even astronomers sometimes pause and double-check what they're seeing. We're going to talk about galaxies. Not just any galaxies, but the most extreme ones ever discovered. The largest, the brightest, the strangest, the ones that seem to bend the rules or quietly ignore them altogether. The kinds of places that make even our own cosmic home, the Milky Way, feel surprisingly ordinary. But before we wander too far out into that enormous darkness, let me ask you something simple. Where are you listening from right now? Maybe you're at home, the lights dimmed, wrapped in a blanket, letting the day slowly fade behind you. Maybe you're lying in bed, staring at the ceiling, waiting for your thoughts to quiet down. Or perhaps you're somewhere else entirely, in a different time zone, at a different hour, arriving here at this exact moment from your own small corner of the world. And what time is it for you right now? It's a funny question, really, because we're about to talk about objects so distant that the light we see from them left billions of years ago. In a sense, every galaxy we'll mention tonight belongs to a completely different now than the one you're experiencing. While you're here, listening, breathing, settling into rest, those galaxies are frozen in the past, quietly shining across unimaginable distances. If you find this kind of slow exploration calming or interesting, or just a nice way to wind down, you might consider giving the video a like, or subscribing. It helps this quiet little space reach more people who might need a gentle pause at the end of their day. Now, I'll do my best not to make this so fascinating that it keeps you awake. But if it does, at least you'll drift off knowing something a little strange about the universe. So get comfortable. Let your thoughts loosen their grip a little. There's no rush here, because somewhere out there, scattered across distances so large they almost stop feeling real, exist galaxies that stretch the limits of what we thought was possible. And to understand just how extreme they are, it helps to begin with something that feels familiar. A galaxy, in simple terms, is a collection of stars, gas, dust, and something much less visible called dark matter, all held together by gravity. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. That's already a number that's difficult to picture. If you tried counting one star per second, it would take you thousands of years just to finish. And yet, in the grand scale of the universe, the Milky Way is not particularly special. It's a spiral galaxy, shaped a bit like a cosmic pinwheel, with long arms winding outward from a dense central region. It rotates slowly, taking about 230 million years to complete a single turn. Somewhere within one of those arms, in a fairly quiet neighbourhood, sits our solar system, orbiting steadily, almost unnoticed. For a long time, galaxies like ours were the template. When astronomers looked out into the sky and catalogued what they saw, spiral galaxies, elliptical galaxies, and a few irregular shapes made up most of the known population. There was a sense, at least for a while, that while galaxies were vast, they followed certain patterns, certain expectations. Big, yes. Complex, absolutely. But still, in some sense, predictable. And then the observations started getting better. Telescopes improved, instruments became more sensitive, and eventually, with projects like the Hubble Space Telescope and later the James Webb Space Telescope, astronomers began to see deeper into space than ever before. What they found wasn't just more galaxies. They found galaxies that didn't quite behave the way they were supposed to. Some were far larger than expected, stretching across millions of light years, containing trillions of stars. Others were so faint and diffuse that they were almost invisible, like ghostly outlines barely holding themselves together. Some formed stars at incredible rates, while others seemed to have stopped entirely, going quiet long before they should have. And then there were the truly puzzling ones. galaxies that appeared too massive for their age, as if they had grown up far too quickly in the early universe. Galaxies that seemed to lack the dark matter we thought was essential for their structure, and others that were almost entirely made of it, glowing faintly only because a few scattered stars gave them away. At first, some of these discoveries were met with skepticism. Maybe the measurements were off. Maybe there was an error in the data. Maybe, as sometimes happens in science, something looked strange simply because we hadn't fully understood it yet. But as more observations came in, from different instruments, from different teams, the pattern became harder to ignore. The universe, it seemed, was not content with neat categories. It was full of extremes. And that brings us to an interesting problem, one that doesn't involve equations or telescopes, but something much closer to home. What does extreme even mean when you're talking about galaxies? On Earth, extremes are relatively easy to define. The tallest mountain, the deepest ocean, the hottest desert. These are things we can compare directly, using familiar scales. We know what it means for something to be twice as tall, or 10 times as hot, or 100 times as deep. But with galaxies, the numbers become so large that our usual sense of comparison starts to break down. Take size, for example. The Milky Way is about 100,000 light-years across. That's already enormous. A light-year, the distance light travels in a single year, is about 9.5 trillion kilometers. Multiply that by 100,000, and you get a number that doesn't really fit into everyday thinking. Now imagine a galaxy 10 times larger than that, or 50 times larger, or more. At some point the word big stops being useful. It becomes more of a placeholder, something we say because we don't have a better way to describe what we're looking at. And yet, astronomers still try. They measure, they compare, they build models and run simulations. They try to understand not just how large or bright or strange these galaxies are, but why they ended up that way in the first place. Because every extreme object in the universe tells a story about how matter moves, how gravity shapes things over time, how the early universe set the stage for everything that followed. Sometimes, those stories fit neatly into what we already know. Other times, they don't. And it's in those moments, when observations don't quite match expectations, that things become especially interesting. Consider this for a moment. When you look up at the night sky, even on a clear dark evening, you're seeing only a tiny fraction of what's actually out there. Most galaxies are far too distant and faint to be seen with the naked eye. Even with powerful telescopes, there are limits to what we can detect, and yet, within that limited view, we've already found galaxies that challenge our understanding, which raises a quiet, slightly unsettling possibility. If the universe we can see already contains so many extremes, what might exist beyond the edge of our observations? What kinds of galaxies are out there, still hidden, still waiting to be discovered? It's a bit like standing on the shore of a vast ocean, noticing that the waves near your feet are already unusual, already unpredictable, and realizing that you haven't even begun to explore what lies further out. And that's where we're heading. Not all at once, of course. There's no need to rush. Instead, we'll move gradually, starting from the kinds of galaxies we understand reasonably well, and then stepping, one example at a time, into more unusual territory. Because before we can fully appreciate just how extreme some galaxies are, it helps to have a sense of what normal looks like. What does a typical galaxy do? How does it form, grow, and evolve over time? And where exactly do things start to deviate from that picture? So, for now, just let that question settle in the background. What counts as ordinary when the universe itself is already so vast and varied? Because once we begin to answer that, the truly extreme galaxies, the ones that stretch size, brightness, and structure to their limits, start to stand out in a very different way. It's a little strange when you think about it, how quickly numbers lose their meaning once they grow large enough. A few seconds feels familiar, a few minutes, still manageable. Even a few hours you can picture that without much effort, but somewhere along the way, As the numbers climb higher and higher, something subtle happens. The mind starts to let go. It stops trying to visualize, and instead, it quietly replaces understanding with a kind of acceptance. Big becomes just big. And in astronomy, that transition happens surprisingly early, because even the most ordinary galaxies are already operating far beyond the scale our intuition was built for. Let's ease into it gently. Imagine standing in a completely dark room and someone hands you a small light. Not bright, just enough to illuminate a single object. Now imagine that object is our sun, just one star, a single steady source of light and warmth. Now picture placing another star beside it, then another, and another. If you kept going, adding stars one by one, you might eventually reach 1,000,000. That alone would be overwhelming. 1,000,000 stars glowing together would fill the room with a brightness that feels almost impossible to ignore. But 1,000,000, in the context of a galaxy, is barely a beginning. The Milky Way contains hundreds of billions of stars, not millions, not even billions, hundreds of billions, each one with its own story, its own planets perhaps, its own quiet processes unfolding over millions or billions of years. And that's just one galaxy. Already the word big starts to feel a little underprepared. Astronomers, of course, don't just rely on words. They measure, they compare, they try to anchor these enormous scales to something concrete. But even with precise numbers, there's always a gap between what we can calculate and what we can truly grasp. Take distance, for example. The Milky Way stretches roughly 100,000 light-years from one side to the other. That means that if you could somehow travel at the speed of light, which is already the fastest possible speed in the universe, it would still take you 100,000 years just to cross it. To put that into a more grounded perspective, modern humans have existed for about 300,000 years. So even at light speed, crossing our own galaxy would take a significant fraction of the entire history of our species. And yet, as large as that sounds, the Milky Way is not among the largest galaxies we know. There are galaxies several times bigger. Some stretch for millions of light years, dwarfing our home galaxy so completely that comparison starts to feel almost symbolic rather than meaningful. And this is where something interesting begins to happen. Because when differences become too large, they stop feeling like differences. If one object is twice as big as another, that's easy to understand. Even 10 times bigger, you can still form a mental picture. But when one galaxy is 10 times, or 100 times, or even 1,000 times larger in certain aspects, the comparison doesn't scale naturally in the mind. It collapses into a single category. Huge. Or maybe just beyond. Astronomers run into this problem all the time. They deal with quantities that don't translate neatly into human experience. So instead of trying to force intuitive understanding, they often shift their approach. They look at relationships instead. How fast does a galaxy rotate? How many stars does it form in a given period? How tightly is it held together by gravity? These questions help create a different kind of picture, one that's less about raw size and more about behaviour. Because sometimes what makes a galaxy extreme isn't just how big it is, but how it acts. Still, size does matter in a very literal sense when it comes to galaxies. Larger galaxies tend to have stronger gravitational pull. That means they can attract and absorb smaller galaxies over time. It's a slow process, unfolding over billions of years, but it happens often enough that many large galaxies are actually the result of countless mergers, each one adding more stars, more gas, more complexity. In that sense, a galaxy's size is like a record of its history. The bigger it is, the more it has likely interacted with its surroundings, pulling in material, growing gradually, sometimes violently. But even this idea has its limits. Because some of the galaxies we've found don't seem to follow that pattern. They're simply too big, too early. Galaxies that appear in the young universe not long after the Big Bang, already showing signs of having formed enormous amounts of mass. According to our standard models, there shouldn't have been enough time for them to grow that large. And yet, there they are. When astronomers first started seeing these objects more clearly, especially with the help of instruments like the James Webb Space Telescope, it raised some uncomfortable questions. If galaxies can become this large so quickly, are our models incomplete? Have we underestimated how efficiently matter can clump together under gravity? Or is there something more subtle going on, something we haven't yet accounted for? These are not questions with immediate answers, and in a way, that's part of what makes them so interesting. Because the moment big stops meaning something precise, it forces us to look deeper, to stop relying on intuition and start building new ways of understanding. But let's slow things down again for a moment. Instead of focusing only on the largest galaxies, it might help to consider how we even define size in the first place. When we say a galaxy is large, what are we actually measuring? Is it the number of stars, the physical diameter, the total mass including invisible components like dark matter? Each of these gives a slightly different answer. A galaxy might be physically large, stretching across a vast distance, but contain relatively few stars. Another might be more compact, yet packed with an incredible number of stars in a smaller volume. So which one is truly bigger? It depends on what you care about. This is one of those subtle complications that doesn't show up in everyday thinking, but becomes important when you're dealing with extremes. Because once you step beyond familiar scales, definitions start to matter more. And sometimes they start to blur. There are galaxies known as ultra-diffuse galaxies, for example, that are almost as large as the Milky Way in terms of diameter, but contain only a tiny fraction of the stars. They're faint, spread out, almost like cosmic shadows. If you were to place one next to the Milky Way, it might look similar in size, but far emptier. So is it big? Yes, in one sense. No, in another. And that ambiguity is everywhere in astronomy. It's not a flaw exactly. More like a reminder that the universe doesn't organise itself according to the categories we prefer. It simply exists, with all its variations, and we do our best to describe it. As you sit here listening, maybe noticing your breathing slow down a little, it's worth remembering that all of this, every galaxy, every star, every distant structure, is part of a single, connected system. The same laws of physics that shape those galaxies also shape the world around you. Gravity pulls things together, energy flows, matter changes form. The difference is scale. And once scale stretches far enough, the familiar becomes unfamiliar again. That's when big stops being a useful word and something else takes its place. Not confusion exactly, more like a quiet acknowledgement that some things aren't meant to be fully pictured, only explored, piece by piece. So, as we continue, keep that in mind. We're not trying to hold the entire universe in a single thought. We're just moving through it slowly, one idea at a time, letting each piece settle before moving on. Because once you let go of the need to fully grasp the size of things, something else becomes easier to notice. Patterns, differences, oddities, and that's where the story becomes more interesting. Because not all galaxies are trying to be the biggest. Some are simply different. And those differences, small at first glance, are where the real surprises begin to show. For a long time, galaxies like ours felt comfortably familiar, at least as familiar as something hundreds of billions of stars wide can ever feel. There's something about a spiral galaxy that gives the impression of order, not rigid, not mechanical, but steady. Predictable enough that, once you understand the general structure, you start to feel like you've got a handle on it. If you've ever seen an image of the Milky Way from above, or more accurately, an artist's reconstruction based on careful measurements, you'll notice that gentle sweeping pattern. A bright central bulge surrounded by long curving arms, winding outward like a slow-moving whirlpool. Not chaotic, not random. There's a kind of rhythm to it, and for decades, astronomers treated spiral galaxies as the baseline, the normal case, the place where things behaved as expected. Stars form in the arms, where gas and dust gather and compress. older stars drift toward the centre. Everything rotates, slowly, steadily, taking hundreds of millions of years to complete a single turn. It's not something you can watch happen in real time, but with enough data, enough observation, the pattern becomes clear. It feels almost peaceful, which is a slightly odd word to use for something so vast, but it fits in a quiet way. Because once you step back from the numbers, from the scales that are too large to fully imagine, what you're left with is motion that doesn't rush. Nothing in a spiral galaxy is in a hurry. Stars orbit at enormous speeds, yes, hundreds of kilometers per second, but over distances so vast that the movement becomes gradual, almost gentle when viewed from afar. It's like watching the hands of a clock move. You know they're in motion, but unless you stare very closely, they seem still. And that sense of steady motion is part of why spiral galaxies became our reference point. If you wanted to understand how galaxies form, you studied spirals. If you wanted to model how stars are born, you looked at their arms. If you wanted to estimate how matter is distributed across a galaxy, you started with a structure like this. It was, in many ways, the comfortable version of the universe, something you could describe, categorize, even predict. But comfort can be misleading, because the more closely astronomers studied these spiral systems, the more they realized that even here, in what seemed like the most orderly type of galaxy, there were details that didn't quite add up. Let's begin with something simple: rotation. You might expect that stars closer to the center of a galaxy would orbit faster than those farther out. After all, that's how things work in our solar system. The planets closer to the Sun move more quickly along their paths, while those farther away take longer to complete an orbit. So it seemed reasonable to assume the same would be true for galaxies, and for a while that assumption held. But then astronomers started measuring rotation speeds more carefully. Instead of slowing down at the edges, as expected, stars in the outer regions of spiral galaxies were moving just as fast as those much closer to the center. This wasn't a small discrepancy. It was consistent across many different galaxies. Something was off. According to the visible matter, the stars, the gas, the dust, there simply wasn't enough mass to keep those outer stars moving at such high speeds without flying away. And yet they stayed, bound, steady, orbiting as if something unseen was holding everything together. That something became one of the most important ideas in modern astronomy: dark matter. It doesn't emit light. It doesn't interact with electromagnetic radiation in any way we can easily detect. But its gravitational influence is unmistakable. Spiral galaxies, the calm, familiar systems we thought we understood, turned out to be embedded in massive halos of invisible matter, extending far beyond the visible structure. In a way, the neat spiral pattern we see is just the bright center of something much larger, mostly hidden from view, and that realization alone shifted the picture quite a bit, because it meant that even our most normal galaxies were only partially understood. There was more going on beneath the surface. Still, despite that hidden complexity, spiral galaxies remained relatively stable environments. Star formation follows certain patterns. Gas flows along the arms. The central region tends to host older stars, sometimes surrounding a supermassive black hole, quietly influencing the motion of everything nearby. It's not static, of course. Nothing in the universe truly is. But compared to what we'll encounter later, spiral galaxies are well behaved. They evolve slowly. They change over time, but not in sudden, dramatic bursts, and that makes them useful. Because before you can recognize something as extreme, you need a sense of what ordinary looks like. You need a reference point, and spiral galaxies provide that. They show us what happens when gravity, gas dynamics, and star formation all interact under relatively stable conditions. They give us a kind of baseline rhythm, but even within that rhythm there are variations. Not all spiral galaxies look exactly the same. Some have tightly wound arms, wrapping closely around the center. Others have looser structures, with arms that stretch farther outward before fading into the surrounding space. Some are rich in gas, actively forming new stars. Others are quieter, with much of their gas already used up, their star formations slowing down over time. And then there are those with central bars, elongated structures of stars and gas extending from the core, altering the flow of material within the galaxy. Each variation adds another layer of complexity. Another reminder that even within what we call normal, there's a wide range of possibilities. As you sit here, maybe feeling a little more settled than a few minutes ago, it's worth noticing how quickly the mind adjusts to these ideas. At first, the scale feels overwhelming. Hundreds of billions of stars, distances measured in light years, invisible matter shaping entire galaxies. But given enough time, even these concepts start to feel manageable. Not fully understood perhaps, but no longer completely out of reach. And that's part of what makes this kind of slow exploration work. You don't need to grasp everything at once. You just let each piece settle, one after another. And over time, a picture begins to form. Now there's something else about spiral galaxies that makes them especially interesting. Something that doesn't immediately stand out in images or measurements. They are in many cases the environments where life has the best chance to develop. Not everywhere within them, of course. The central regions can be crowded, energetic, sometimes hazardous. The outer edges might be too sparse, lacking the necessary materials, but somewhere in between, in those quiet spiral arms, conditions can become just right. Stars like our sun form. Planets take shape. Stable orbits allow time for complex processes to unfold, and over billions of years, in at least one known case, those processes lead to something capable of looking back out at the galaxy and asking questions about it. That alone makes spiral galaxies feel a little more personal. Not small, not simple, but familiar in a different way. They're not just distant structures, they're places where things can happen, where time can pass in ways that allow complexity to emerge. And that familiarity, that sense of home, is part of why they held such an important place in our understanding for so long. They weren't just one type of galaxy among many, they were the type we knew best. But as observations improved, as telescopes looked deeper and further, it became clear that not all galaxies followed this calm, steady pattern. Some were far larger, some far more chaotic. Some formed stars at rates that made spiral galaxies seem almost idle by comparison. Others had already burned through their fuel, going quiet long before expected, and gradually the idea of a typical galaxy began to blur. Spiral galaxies didn't disappear from the picture, of course. They remain common, and in many ways they still represent a kind of balance between order and complexity. But they were no longer the whole story. They were just one chapter in a much larger narrative. And once you start looking beyond that chapter, once you allow for the possibility that galaxies can behave in ways that don't fit neatly into familiar patterns, the universe begins to open up in a different way. Because the extremes, the truly unusual galaxies, don't just differ in size or shape. They challenge the assumptions built from studying these calmer systems. They raise questions about how galaxies grow, how quickly they can form, how they interact with their surroundings, and what limits, if any, actually exist. So as we move forward, keep that image of a spiral galaxy in mind. Not as something simple, but as something steady, a kind of quiet reference point. At some point, even after you've adjusted to the idea that galaxies are already enormous, there comes a moment where the scale shifts again. Not gradually, not in a way that feels like a smooth extension of what you already understand, but more like a quiet step beyond it. Because once astronomers began cataloguing galaxies in greater detail, comparing them across larger surveys and deeper observations, it became clear that some of them weren't just bigger than average. They were in a completely different category. And the interesting part is that you don't notice it right away. If you look at images of galaxies, even the largest ones don't immediately announce themselves as something extreme. They still have familiar shapes, elliptical glows, sometimes faint halos, occasionally hints of structure. Nothing about them looks exaggerated in the way you might expect. But then you see the numbers, and that's where the shift happens. Take a moment to recall the scale we've already discussed. The Milky Way stretches roughly 100,000 light-years across. That's already enough to challenge any comfortable sense of size. It contains hundreds of billions of stars, each separated by vast distances, all bound together in a structure that takes hundreds of millions of years just to rotate once. Now imagine something 10 times wider, 1,000,000 light-years across. Then imagine something larger still, because there are galaxies that don't just exceed the Milky Way by a factor of 2 or 3, but by 10, 20, sometimes even more, depending on how you measure them. And when you place those numbers side by side, the word large stops being particularly helpful. Astronomers have a name for some of these objects. They're called giant elliptical galaxies, and at the extreme end, supergiant ellipticals. Unlike spiral galaxies, which have those well-defined arms and sense of rotation you can almost picture, elliptical galaxies are more like vast glowing clouds of stars. They lack the neat structure of spirals. Instead, their stars move in more random orbits, creating a smooth, rounded appearance. But what they lack in structure, they make up for in scale. One of the most well-known examples is EC 1101, often described as one of the largest galaxies ever discovered. It sits at the centre of a massive galaxy cluster, and its size is difficult to put into perspective. Estimates suggest it spans around 6 million light-years. That's not a typo. 6 million! If you were to place the Milky Way inside it, you wouldn't just fit one copy. You could fit dozens of Milky Way-sized galaxies across its diameter, with space to spare. But even that comparison doesn't fully capture what's going on, because galaxies like IC 1101 aren't just larger versions of spirals or smaller ellipticals. They're the result of long, complex histories involving repeated mergers. Over billions of years, smaller galaxies fall toward the centre of a cluster, drawn in by gravity. When they get close enough, they don't simply pass by. They interact, they distort, and eventually they merge. Each merger adds more stars, more mass, more volume. And over time, those accumulated pieces form something much larger than any one galaxy could have become on its own. So when you look at a giant elliptical galaxy, you're not just seeing a single object, you're seeing the outcome of countless past interactions, a kind of cosmic archive built from the remnants of many smaller systems. There's something quietly unsettling about that idea. Not in a dramatic way, but in the sense that these galaxies are less like individual structures and more like collections of histories layered on top of each other. Stars that once belonged to separate galaxies now orbit within the same vast halo, their origins almost impossible to trace, and the process doesn't really stop. Even now, galaxies continue to merge. Even now, these giant ellipticals continue to grow. But growth at this scale is slow, extremely slow. From a human perspective, nothing appears to change. The galaxy looks stable, almost timeless. But over billions of years, it's still evolving, still absorbing, still becoming something slightly larger than it was before. Now, there's another detail that makes these galaxies even more interesting. They're often found at the centres of galaxy clusters. A galaxy cluster is exactly what it sounds like. A collection of galaxies bound together by gravity. Some clusters contain hundreds, even thousands of galaxies, all moving within a shared gravitational environment. At the very centre of many of these clusters sits a dominant galaxy, larger and more massive than the rest. These are sometimes called brightest cluster galaxies, or BCGs, and they tend to be the largest galaxies we know. The reason for this is fairly straightforward, at least in principle. The centre of a cluster is where gravitational pull is strongest. It's where galaxies are most likely to drift inward over time, and when they do, they're more likely to merge with whatever is already there. So the central galaxy acts like a kind of collector, not actively, not deliberately, but inevitably. Over billions of years it accumulates mass, growing larger and larger as more galaxies fall into its reach. But even with that explanation, there's still something that doesn't quite sit comfortably. Because if you follow the logic through, you might expect there to be some upper limit. At some point, perhaps, galaxies should stop growing. The supply of nearby galaxies should run out. The rate of mergers should slow down. And yet, when we look out into the universe, we keep finding objects that push those expectations further. Larger, more massive, more extended. It raises a quiet question. Is there a maximum size for a galaxy? Or does the process simply continue as long as the conditions allow? At the moment, we don't have a definitive answer. There are practical limits, of course. The expansion of the universe means that over very long timescales, distant galaxies move away from each other, making future mergers less likely. Local environments matter. The density of galaxies in a cluster plays a role. But within those constraints, the range of galaxy sizes is broader than we once thought. And that brings us back to that earlier idea. The moment when big stops meaning anything precise. Because with galaxies like IC 1101 or others of similar scale, you reach a point where comparisons stop helping. It's not just that they're larger than the Milky Way, it's that they operate on a scale where our usual reference points no longer apply. As you sit here, perhaps feeling a little more relaxed, it's worth noticing how the mind handles this. At first, there's a tendency to try and picture it, to imagine a galaxy millions of light years across, to place it side by side with something more familiar. But after a while, that effort softens. You don't need to hold the entire image in your head. You can let the numbers sit there, quietly, without forcing them into a clear mental picture. Because understanding doesn't always require visualization. Sometimes it's enough to recognize the relationships. This galaxy is larger than that one. This system has grown through mergers. This structure sits at the center of something even bigger. And that's another important detail. Even the largest galaxies are not isolated. They exist within larger frameworks, clusters, superclusters, the cosmic web itself. So no matter how large a galaxy becomes, it's still part of something else. Still one piece in a much larger arrangement. And that perspective shifts things slightly. It reminds you that extreme is always relative. A galaxy can be enormous by our standards, yet still be just one component in a structure that stretches even further. There's a certain comfort in the idea that the universe takes its time, that everything, no matter how large or complex, builds gradually. Stars form from clouds of gas, galaxies grow through mergers, structures assemble step by step over billions of years. It's a slow process, steady enough that, given enough patience, you can begin to trace how one stage leads to the next. And for a long while, that picture held together quite well. Galaxies, especially the largest ones, were expected to grow over time. Small systems formed first, merging and accumulating matter until they became the massive galaxies we see in the present-day universe. It made sense, it matched the models, it fit the timeline. But then something started to appear in the data, something that didn't quite follow that sequence. Galaxies that were simply too big, too early. To understand why that's surprising, it helps to slow things down and consider how we actually look into the universe. When astronomers observe distant galaxies, they're not seeing them as they are now. They're seeing them as they were when their light first began its journey toward us. Because light takes time to travel, the farther away an object is, the further back in time we're looking. So when we observe galaxies billions of light years away, we're effectively looking into the early universe, a time when everything was younger, less developed, still in the process of forming, and according to our best models, galaxies at that stage should be relatively small, not empty, not insignificant, but still growing, still assembling, certainly not massive enough to rival the largest galaxies we see today. And yet, when instruments like the James Webb Space Telescope began sending back detailed observations, astronomers started noticing something unexpected. Some of those early galaxies didn't look small at all. One of the most discussed examples carries a name that doesn't immediately suggest anything extraordinary. GN-Z11. It doesn't sound dramatic, just a catalogue designation, one among many. But what makes GN-Z11 unusual isn't its name, it's where and when it exists. GN-Z11 is observed at a time when the universe was only about 400 million years old. To put that into context, the universe today is roughly 13.8 billion years old. So we're looking at a galaxy that formed when the universe was still in its very early stages, barely beginning to organise itself into the structures we recognise. And yet, GN-Z11 is not small. It's already forming stars at a significant rate. It already contains a substantial amount of mass. It's already behaving like a galaxy that, according to earlier expectations, should not yet have had time to reach that level of development. Now, it's important to be careful here. GN-Z11 is not necessarily the largest galaxy ever discovered. It's not an enormous giant like the ones we discussed earlier. What makes it remarkable is the combination of its size, its activity, and its age. It exists earlier than it should, and it's more developed than expected. Which raises a quiet but persistent question. How did it get there so quickly? Because in the standard picture of galaxy formation, structures grow through a process often called hierarchical assembly. Small clumps of matter form first, then merge, gradually building larger systems over time. It's a bit like assembling something piece by piece. You start small, add components, and eventually end up with something much larger. But GN-Z11 and other galaxies like it seem to have skipped part of that process, or at least they've compressed it into a much shorter timescale. Instead of taking billions of years to reach a certain level of mass and activity, they appear to have done it in a few hundred million. And that's where things become interesting. Because when observations don't match expectations, there are usually two possibilities. Either the observations are incomplete, or the model needs adjusting. In this case, the observations have been confirmed multiple times, using different methods, different instruments. So attention turns to the models. Maybe galaxies can form more quickly than we thought. Maybe the early universe provided conditions that allowed matter to clump together more efficiently. Perhaps there were regions of higher density, where gas and dark matter collapsed faster, accelerating the growth of galaxies in those areas. Or maybe something else is happening, something we haven't fully accounted for yet. There are even suggestions that our estimates of mass and star formation rates in these early galaxies might need refinement. After all, interpreting faint distant light is not a simple task. There are uncertainties, assumptions, corrections that need to be applied. But even with those uncertainties, the overall pattern remains. We are finding galaxies that seem to have grown up too fast, and GN-Z11 is not alone. There are others detected in deep field surveys, some even more puzzling, showing signs of being massive and structured at times when the universe should still have been in its early stages of assembly. As you sit here, perhaps noticing your thoughts slowing down a little, there's something quietly fascinating about this. Not in a dramatic, urgent way. More in the sense of a puzzle that doesn't quite fit, because it reminds you that our understanding of the universe is always provisional, always open to revision. We build models based on what we observe, but those models are only as complete as the data available at the time. And when new observations come in, especially ones that challenge the existing framework, they don't break science. They refine it. They push it forward. They ask us to look again, to think more carefully, to consider possibilities that weren't obvious before. Now, there's another layer to this. It's not just about size or mass, it's about time. Because these galaxies don't just appear large, they appear mature. They show signs of ongoing star formation, structured behaviour, sometimes even hints of organised dynamics. Things that, in earlier models, required longer periods to develop, and yet, here they are, already in place. Which leads to a slightly different way of thinking about the problem. Maybe it's not that these galaxies are too big. Maybe it's that our sense of how quickly things can happen in the universe needs to be adjusted. Because when you consider the conditions of the early universe, it wasn't a quiet place. It was dense, hot, filled with matter that hadn't yet spread out as much as it has today. In such an environment, gravitational interactions could happen more rapidly. Gas clouds could collapse faster. Star formation might proceed at a much higher rate. So what seems fast to us might simply be normal under those conditions. It's just that we're used to observing a universe that has already expanded and cooled, where processes unfold more slowly. Still, even with that consideration, the existence of galaxies like GN-Z11 continues to challenge our assumptions. Not dramatically, not in a way that overturns everything we know, but enough to keep things interesting, enough to remind us that there are still details to uncover. There's an interesting shift that happens once you move away from the idea that galaxies are defined by how bright or dense they appear. Up to now, the extremes we've explored have leaned toward more stars, more mass, more activity, more speed, bigger, faster, earlier. It's a natural way to think about the universe, because those are the kinds of differences that stand out immediately. But not everything unusual announces itself that way. Some galaxies go in the opposite direction. Not brighter, but fainter. Not denser, but thinner. Not crowded with stars, but spread so widely that, at first glance, they barely seem to be there at all. And these are some of the most quietly surprising objects we've found. They're called ultra-diffuse galaxies. The name sounds technical, but it's actually quite literal. Ultra-diffuse simply means that their stars are spread out over a very large area, so thinly distributed that the entire galaxy has a very low surface brightness. In simpler terms, even though they can be enormous, they're incredibly faint. So faint, in fact, that for a long time we didn't notice them. That's one of the more subtle things about astronomy. It's not just about looking further into space. It's also about learning how to see things that don't stand out. Objects that don't shine brightly, that don't draw attention to themselves, that blend into the background. Ultra-diffuse galaxies fall into that category. If you were to place one of these galaxies next to something like the Milky Way, the comparison would be surprising. In terms of size, they can be similar. Some of them stretch tens of thousands of light years across, comparable to the diameter of a large spiral galaxy. But instead of containing hundreds of billions of stars, they might have only a few billion, or even less. The result is something that feels almost like a cosmic outline, a galaxy with the right shape, the right scale, but missing most of the brightness you would expect. If you could somehow see one up close standing within it, the night sky might look very different. The stars would be much farther apart. The overall glow would be faint, almost ghostly. You might see individual stars, but not the dense, luminous band we associate with the Milky Way. It would feel quiet, not empty, but subdued. And that's part of what makes these galaxies so interesting, because they challenge a basic assumption, that size and brightness go together. In most galaxies they do. Larger galaxies tend to have more stars, more gas, more everything, but ultra-diffuse galaxies break that pattern. They have the size without the substance, at least in terms of visible matter. One of the most well-known examples is Dragonfly 44. The name comes from the instrument that helped identify it more clearly, the Dragonfly Telephoto Array, a telescope designed specifically to detect faint extended objects. Dragonfly 44 sits in the Coma Cluster, a dense region of space filled with galaxies. At first, it might seem like just another faint smudge among many. But when astronomers studied it more closely, they found something unexpected. Despite its faint appearance, Dragonfly 44 is roughly the same size as the Milky Way. That alone would be unusual, but the real surprise came when scientists tried to estimate its mass. Based on the motion of stars within the galaxy, it appeared that Dragonfly 44 contains a significant amount of mass, far more than what could be accounted for by its visible stars alone. In other words, it seems to be dominated by dark matter. In fact, at one point, estimates suggested that over 99% of its mass could be dark matter, making it one of the most dark matter-dominated galaxies ever observed. Now, It's worth noting that measurements like these can be refined over time. Different observations, different methods can lead to updated estimates. But the overall picture remains. Dragonfly 44 is large, faint, and heavily influenced by something we cannot see. And that combination raises a number of questions. How does a galaxy like this form? Why didn't it produce more stars? If it has so much dark matter, why is the visible component so sparse? There are a few ideas. One possibility is that ultra-diffuse galaxies formed in environments where star formation was somehow suppressed. Perhaps strong bursts of energy from supernovae or active galactic nuclei pushed gas out of the galaxy early on, preventing it from forming many stars. Another idea is that these galaxies experienced interactions with their surroundings, especially in dense clusters like Coma. Gravitational forces from nearby galaxies or from the cluster itself might have stretched them out, pulling their stars into a more diffuse configuration. There's also the possibility that they formed with a large amount of dark matter to begin with, creating a gravitational framework that allowed them to remain intact even with relatively few stars. Because that's another important point. Even though ultra-diffuse galaxies are faint, they are not fragile in the way you might expect. If Dragonfly 44 really is dominated by dark matter, that invisible mass provides the gravitational glue that holds the galaxy together. Without it, the sparse collection of stars would likely drift apart over time. So in a sense, these galaxies are held together by something we can't directly observe. They're shaped by an unseen structure, with just a thin scattering of stars tracing out its presence. That's where the idea of them being ghostly comes from. Not because they're unreal, but because they're so difficult to detect, so faint that they almost slip through our observational net. And that leads to an interesting possibility. If these galaxies are hard to see, how many of them are out there? For every bright, well-defined galaxy we observe, there could be many more ultra-diffuse systems that simply haven't been detected yet. Galaxies that exist quietly in the background, contributing to the overall structure of the universe without drawing much attention. It's a reminder that our view of the cosmos is shaped not just by what exists, but by what we're able to detect. And detection in astronomy is not always straightforward. Brightness matters. Contrast matters. The ability to distinguish an object from the surrounding background matters. Ultra-diffuse galaxies challenge all of those. They force astronomers to develop new techniques, new instruments, new ways of processing data, just to bring these faint structures into view. As you listen, perhaps noticing how your thoughts have slowed into a steadier rhythm, there's something quietly fitting about that. Because these galaxies themselves don't demand attention. They don't shine brightly. They don't erupt with activity. They simply exist, spread thin across space, almost blending into the darkness. And yet, they carry important information. About dark matter, about galaxy formation, about the range of structures that can exist under the same physical laws. They show that a galaxy doesn't need to be bright or dense to be real. It can be vast and faint at the same time, structured and elusive, present but easy to overlook. And once you start to notice them, once you accept that galaxies can take this kind of form, it changes the way you think about what's out there. Because if something as large as Dragonfly 44 can remain so faint, so difficult to detect, then the universe may contain many more surprises hidden just beyond the edge of what we can easily see. Not because they're far away, but because they're quiet. Some discoveries don't arrive with a sense of scale or brightness, but with a quiet contradiction. They don't stretch across millions of light years, and they don't outshine entire clusters. Instead, they sit there in the data, calmly existing, while subtly disagreeing with something we thought we understood. Galaxies with almost no dark matter fall into that category. To see why that's unusual, it helps to revisit something that, until recently, felt almost certain. Dark matter isn't just a small detail in astronomy, it's one of the main ingredients. When astronomers study how galaxies rotate, how they hold themselves together, how they form and evolve, dark matter shows up again and again as the invisible framework that makes it all possible. Without it, many galaxies shouldn't be stable. Their stars would move too fast, drift too far, eventually escaping the galaxy's gravitational pull. So the idea that a galaxy could exist with little to no dark matter is unexpected. Not impossible, at least not according to the laws of physics, but surprising enough that when the first strong candidate appeared, it drew a lot of attention. One of the most well-known examples is NGC 1052-DF2. The name itself is, again, unassuming. A catalogue entry, nothing more. But what makes this galaxy interesting isn't how it looks at first glance. It's what happens when you start measuring how its stars move, because motion reveals mass. When astronomers observe a galaxy, they often track the velocities of stars or star clusters within it. Faster movement usually indicates a stronger gravitational pull, which in turn suggests more mass. In most galaxies, those measurements reveal more mass than can be accounted for by visible matter alone. That extra mass is attributed to dark matter. But in the case of NGC 1052-DF2, something different showed up. The stars and star clusters within this galaxy were moving more slowly than expected. Slow enough that their motion could be explained almost entirely by the visible matter, the stars themselves, without needing to invoke a large amount of dark matter. At first, this was puzzling. Then it became controversial. Because if the measurements were correct, this galaxy didn't just have less dark matter than usual, it had almost none. And that raises an interesting question. If dark matter is supposed to be essential for galaxy formation, how does a galaxy like this exist at all? There are a few possible explanations, and none of them are completely settled. One idea is that NGC 1052-DF2 might have formed in an unusual environment, perhaps influenced by nearby galaxies in a way that stripped away its dark matter over time. Gravitational interactions can be complex, especially in dense regions where galaxies pass close to one another. In such encounters, it's possible for material to be pulled out, redistributed, or even separated in ways that aren't immediately obvious. Another possibility is that this galaxy formed from gas that was somehow ejected during past interactions, forming a new system without inheriting much dark matter in the process. This kind of object is sometimes referred to as a tidal dwarf galaxy, created from the debris of larger galaxies colliding and interacting. If that's the case, then NGC 1052-DF2 might not be missing dark matter in the usual sense. It might simply have formed without it. But even that explanation raises questions, because if galaxies can form in this way, then the role of dark matter becomes more nuanced. Not universal perhaps, but context-dependent. There's also the possibility that the measurements themselves need refinement. Astronomy, especially at these distances, involves careful interpretation of faint signals. Small uncertainties can lead to different conclusions, and over time, new observations can either reinforce or challenge initial findings. In fact, follow-up studies of NGC 1052-DF2 and similar galaxies have sparked ongoing debate, with some teams suggesting that the distance to the galaxy might have been misestimated, which would affect calculations of its mass. Others have found additional galaxies in the same region that appear to share similar properties, suggesting that this might not be an isolated case, and that's where things become especially interesting. Because if there are multiple galaxies with little to no dark matter, then this isn't just a one-off anomaly. It's a pattern. A small one, perhaps, but enough to make astronomers pause. As you sit here, maybe feeling your thoughts settling into a slower rhythm, there's something quietly intriguing about that, because it shows how science handles uncertainty. Not with sudden conclusions, but with careful observation, repeated measurements, and ongoing discussion. Nothing is rushed. Ideas are tested, challenged, refined, and sometimes a single unexpected result opens the door to entirely new ways of thinking. Now, step back for a moment and consider the contrast. In the previous part, we explored galaxies that seem to be dominated by dark matter, where the visible stars are just a faint trace of a much larger unseen structure. Here, we're looking at the opposite. Galaxies where the visible matter appears to be almost all there is. Two extremes sitting side by side, one heavily influenced by something invisible, the other seemingly almost free of it. And both exist within the same universe, governed by the same fundamental laws. That alone suggests that galaxy formation is more flexible than we once assumed. That there isn't just one pathway, one standard model that applies uniformly to everything. Instead, there are variations, different starting conditions, different interactions, different outcomes, and sometimes those outcomes land at the edges of what we expect. There's also something else worth noticing. These galaxies, despite their unusual properties, don't look dramatically different at first glance. NGC 1052-DF2, for example, is faint and diffuse, similar in appearance to the ultra-diffuse galaxies we discussed earlier. If you didn't measure the motion of its stars, you might not realize anything was unusual, which means that the universe can hide its most interesting features in plain sight. Not through distance or brightness alone, but through subtle differences in behavior. And that's a reminder that observation isn't just about seeing, it's about measuring, comparing, interpreting. Looking not just at what is visible, but at how things move, how they interact, how they fit into the larger picture. As we move forward, that idea becomes more important, because the extremes we're exploring aren't always obvious. Some are bright and dramatic, others are quiet, almost easy to overlook. But each one adds another piece to the puzzle, another hint that the universe is more varied, more adaptable than our simplest models suggest. And once you accept that galaxies can exist with almost no dark matter, it becomes easier to consider the full range of possibilities. Not just galaxies that lack something we expected, but galaxies that take familiar processes and push them to their limits, forming stars at rates that seem almost excessive, burning through their material far faster than typical systems. Across the range of galaxies we've explored so far, there's been a kind of balance. Even when something unusual appears, whether it's a galaxy that formed too quickly or one that seems to lack dark matter, there's still a sense that visible matter plays a central role. Stars, gas, dust. These are the things we see, measure, and use as anchors for understanding. But that balance doesn't always hold, because there are galaxies where the visible part is almost an afterthought. Not entirely absent, but so minimal compared to the total mass that it barely registers. And in those cases, what you're really looking at is something dominated almost completely by dark matter. To ease into this idea, it helps to return briefly to something familiar. In a typical galaxy like the Milky Way, dark matter forms a halo that extends far beyond the visible stars. The stars orbit within that halo, their motion shaped by its gravitational pull. Even though we can't see the dark matter directly, we can infer its presence from the way stars move. So the visible galaxy, the part we can observe with telescopes, is really just the central luminous region of a much larger structure. Now imagine taking that idea and pushing it further. Imagine a system where the dark matter halo is still there, still massive, still dominant, but the visible component is reduced to a faint scattering of stars, or in some cases almost nothing at all. What you're left with is something that behaves like a galaxy in terms of gravity, but barely qualifies as one in terms of what we can actually see. One of the clearest examples of this comes from a class of objects known as dwarf spheroidal galaxies. These are small, faint galaxies that orbit larger ones, often found in the outskirts of systems like the Milky Way. At first glance, they don't look particularly remarkable. They're dim, lacking the bright structure of spirals or the smooth glow of ellipticals. But when astronomers measure the motion of stars within these galaxies, something unusual emerges. The stars move much faster than expected based on their visible mass alone. In some cases, the discrepancy is extreme. The visible matter, the stars we can count, accounts for only a tiny fraction of the total mass required to keep the galaxy bound together. The rest must be something else, something invisible. A well-known example is Segway 1. Segway 1 is not large. In fact, it's one of the smallest galaxies known. It contains only a few hundred to a few thousand stars, depending on how you define its boundaries. If you were to look at it without context, it might not even register as a galaxy at all. It's that faint. And yet, when astronomers studied the velocities of those stars, they found that Segway 1 is incredibly massive for its size. So massive, in fact, that it appears to be one of the most dark matter-dominated objects ever discovered. Estimates suggest that more than 99% of its mass is dark matter, which leads to an unusual conclusion. In Segway 1, the stars are not the main component. They're more like tracers, tiny points of light embedded within a much larger invisible structure. It's as if the galaxy itself is mostly dark matter, and the stars are just a thin layer on top, enough to make it detectable, but not enough to define it. That idea shifts the way you think about what a galaxy is. Because traditionally, a galaxy is something you see, a collection of stars forming a recognizable structure. But in cases like this, the visible part is almost incidental. The real structure, the thing that holds everything together, is something we can't observe directly. And that raises a quiet question. How many such systems are out there? Because if a galaxy can exist with only a handful of stars, just enough to reveal its presence, then there could be many more that are even fainter. Structures made almost entirely of dark matter, with so few stars that they're nearly impossible to detect with current instruments. In other words, what we see might be only a small fraction of what actually exists. As you sit here, perhaps noticing how the ideas are settling in more gently now, there's something almost calming about that thought, not in the sense of certainty, but in the sense of openness. The universe isn't limited to what we can easily observe. It extends beyond that, into regions and structures that require indirect methods to understand. And dark matter-dominated galaxies are a good example of that. They remind us that visibility is not the same as importance. Something can be faint, almost hidden, and still play a major role in the structure of the cosmos. There's also a broader implication here. If dark matter can form stable structures on its own, with only minimal visible matter, then it might be doing more than just supporting galaxies. It might be shaping the large-scale structure of the universe in ways that go beyond our current understanding. In fact, when astronomers simulate the formation of galaxies using computer models, dark matter often appears as the scaffolding on which everything else builds. Gas falls into dark matter halos, cools, forms stars, and gradually creates the visible galaxies we observe. But if the dark matter halo forms first, and the visible matter only sometimes follows, then it's possible to have halos without much visible content. Galaxies in a gravitational sense, but not in a luminous one. And that brings us back to the idea of extremes. Because while some galaxies challenge our expectations by lacking dark matter, others challenge them by having almost nothing else. Two ends of a spectrum. On one side, galaxies where visible matter dominates. On the other, galaxies where dark matter is almost everything. And in between, a wide range of possibilities. This variety is what makes the study of galaxies so rich. It's not just about finding the biggest or the brightest, it's about understanding the full range of structures that can exist under the same physical laws. Not every galaxy takes its time. Up to this point, there's been a kind of quiet rhythm to everything we've explored. Galaxies forming gradually, growing over billions of years, stars appearing here and there as gas slowly gathers and collapses. Even when things became unusual, even when galaxies were too large or too faint or missing something we expected, there was still a sense of patience in how they evolved. But that rhythm doesn't apply everywhere. Some galaxies don't form stars at a steady pace. They don't spread the process out over billions of years. Instead, they compress it into something much more intense. They burn bright, fast, and almost relentlessly. And for a relatively brief period, at least on cosmic timescales, they become some of the most active places in the entire universe. These are known as starburst galaxies. The name itself is quite literal, a burst of star formation, far beyond what you would expect under normal conditions. To understand how unusual this is, it helps to start with something familiar again. In the Milky Way, new stars form at a modest rate. On average, our galaxy produces roughly 1 to a few new stars per year. That might sound like a lot, but given the scale of the galaxy, it's actually quite gentle. Gas clouds drift. Gravity pulls them together. Over time, small regions collapse and ignite, forming new stars. It's a steady, ongoing process, balanced enough that the galaxy can sustain it for billions of years. Now imagine increasing that rate dramatically, not by a factor of 2 or 3, but by 10, 100, sometimes even more. Instead of forming a few stars per year, a starburst galaxy might form dozens, hundreds, or even thousands, all at once, all across large regions of the galaxy. The difference is not just quantitative, it's qualitative. Because when star formation happens that quickly, it changes the environment itself. Gas is consumed at a rapid pace. Massive stars form in large numbers, and those stars don't live very long. They burn hot and fast, ending their lives in powerful supernova explosions. Each explosion releases enormous amounts of energy, pushing gas outward, heating the surrounding material, and sometimes triggering even more star formation in nearby regions. It becomes a feedback loop. More stars lead to more explosions, which lead to more compression of gas, which leads to more stars, at least for a while. One of the most well-known examples of this kind of activity is Messier 82, often called the Cigar Galaxy. Messier 82 sits relatively close to us, in astronomical terms, interacting gravitationally with a neighbouring galaxy, Messier 81. That interaction is important, because starburst activity often isn't random, it's triggered. When galaxies pass near each other, or collide, or even just exert strong gravitational influence, their internal gas can become disturbed. Clouds that were once stable begin to compress. Regions that were quiet suddenly become active. In Messier 82, this interaction has driven an intense period of star formation. If you observe it in visible light, it already looks active, with bright regions scattered throughout. But if you look in other wavelengths, especially infrared and X-ray, the picture becomes even more dramatic. You can see vast outflows of gas being pushed out of the galaxy, driven by the combined energy of supernova explosions and stellar winds from massive stars. These outflows extend thousands of light years into space, forming something like a galactic wind. It's as if the galaxy is breathing, expelling material as quickly as it forms new stars. And that's part of what makes starburst galaxies so interesting. They're not stable in the long term, they can't be, because forming stars at such a high rate consumes gas very quickly. The fuel runs out, the burst ends, and the galaxy transitions into a quieter phase, sometimes leaving behind a very different structure than it started with. So in a sense, a starburst galaxy is a temporary state, a phase in a galaxy's life, rather than a permanent condition. But during that phase, everything is amplified. Brightness increases dramatically. Energy output rises. The entire galaxy becomes more active, more luminous, more intense. Some starburst galaxies are so bright in infrared light that they outshine entire clusters of galaxies in certain wavelengths. These are sometimes referred to as ultra-luminous infrared galaxies, or ULIRGs. In these systems, dust plays a major role. The intense star formation produces a lot of dust, which absorbs visible light and re-emits it in the infrared. So even if the galaxy looks obscured in optical images, it can be incredibly bright in other parts of the spectrum. This is another reminder that what we see depends on how we look. A galaxy might appear dim or chaotic in one wavelength and overwhelmingly bright in another. As you listen, perhaps noticing how your breathing has slowed just a little, there's something almost rhythmic about this process. Not calm exactly, but patterned. A build-up of activity, a peak, and then a gradual decline. like a kind of cosmic cycle. Quiet periods followed by bursts of intensity, then a return to something more stable. And that pattern isn't limited to individual galaxies. It appears across different scales: star formation in small regions, starburst activity in entire galaxies, even larger structures evolving over time, everything connected by the same underlying physics: gravity, energy, motion. Now, there's another aspect of starburst galaxies that makes them particularly important. They can shape their surroundings. Those powerful outflows we mentioned earlier don't just affect the galaxy itself. They push gas into intergalactic space, enriching it with heavier elements produced in stars. This material can later become part of other galaxies, or contribute to future star formation elsewhere. So a starburst galaxy doesn't just consume its own gas, it redistributes matter, it influences the environment around it. In that sense, these galaxies act like engines, not quiet ones, but active dynamic systems that drive change beyond their own boundaries. And yet, despite all this intensity, the starburst phase doesn't last very long. On cosmic timescales, it's brief. Maybe tens of millions of years, sometimes a few 100 million. After that, the gas supply diminishes, the rate of star formation drops, and the galaxy settles into a quieter state. What remains is a record of that activity, a population of stars formed in a relatively short period, outflows that have reshaped the surrounding space, and sometimes a central region that has become more compact or more evolved. It's almost like a galaxy going through a period of rapid growth, using up its resources quickly and then slowing down afterward. And that idea connects back to something we touched on earlier: galaxies that formed too quickly, galaxies that appear more developed than expected at early times. Starburst activity could be part of that explanation. If a galaxy undergoes an intense period of star formation early in its history, it could build up mass and structure much faster than a more gradual process would allow. So these extreme bursts might not just be interesting on their own, they might help explain other extremes. As we continue, that connection becomes more important. Because the universe doesn't present its phenomena in isolation. Different processes interact, overlap, influence one another. Fast formation, intense starbursts, unusual structures, all part of the same larger picture. And once you've seen a galaxy that forms stars at such an extraordinary rate, it becomes easier to understand how some galaxies might burn through their fuel completely. At some stage in their long existence, galaxies begin to quiet down. Not suddenly, not in a dramatic instant, but gradually, almost imperceptibly at first. The bright regions where stars once formed begin to fade. The dense clouds of gas that once collapsed into new suns grow thinner, more dispersed or simply run out, and eventually something subtle but profound happens. Star formation stops. When that process ends, a galaxy doesn't disappear. It doesn't fall apart or vanish into darkness. All the stars that already exist continue shining, orbiting, aging in their own time, but no new stars take their place. In that sense, the galaxy becomes still. Astronomers often describe these systems as quenched galaxies, or more informally, dead galaxies. The word sounds a bit dramatic, but it points to something specific. Not death in the sense of destruction, but the end of activity, the end of growth. Because in most galaxies, the ongoing formation of stars is what gives them a sense of life. Gas flows, collapses, ignites, new light appears, the structure evolves. Without that, the galaxy enters a different phase. One of the most well-known examples of this kind of system is Messier 87, often abbreviated as M87. M87 sits at the centre of the Virgo cluster, surrounded by hundreds of other galaxies. It's large, massive, and at first glance quite luminous. But its brightness comes mostly from older stars. Stars that formed long ago and have been shining steadily ever since. What's missing is significant new star formation. If you were to compare M87 to a spiral galaxy like the Milky Way, the difference would be clear, not in shape alone, but in activity. The Milky Way still forms stars slowly but continuously. Regions of gas collapse, new stars ignite, and the galaxy maintains a kind of ongoing renewal. M87 does not. Its gas supply is either gone, too hot, or otherwise unavailable for forming new stars. The processes that once fueled its growth have largely come to an end. So what causes that shift? Why do some galaxies stop forming stars altogether? There isn't just one answer, but there are several mechanisms that seem to play a role. One of the most important involves energy. In galaxies like M87, the central region often hosts a supermassive black hole, an object millions or even billions of times more massive than the Sun. When material falls into that black hole, it doesn't simply disappear quietly. It can release enormous amounts of energy in the process, heating the surrounding gas. Hot gas behaves very differently from cold gas. Cold gas can collapse under gravity, forming dense regions that eventually ignite into stars. Hot gas, on the other hand, resists collapse. It spreads out, becomes less dense, and is far less likely to form new stars. So if a galaxy's gas is heated sufficiently, star formation can slow down or stop entirely. In M87, this effect is particularly noticeable. The galaxy's central black hole, famously imaged by the Event Horizon Telescope collaboration, produces powerful jets of energy that extend far beyond the core. These jets interact with the surrounding gas, heating it and preventing it from cooling and collapsing. In a sense, the galaxy's own centre contributes to shutting down its future growth. Another factor is environment. Galaxies in dense clusters, like the Virgo cluster where M87 resides, are subject to interactions with their surroundings. As they move through the hot diffuse gas that fills the cluster, they can lose their own gas through a process known as ram pressure stripping. Imagine a galaxy moving through a medium like a car driving through rain. The faster it moves, the more force is exerted on it by the surrounding material. In the case of galaxies, that force can strip away gas, removing the very material needed for star formation. Over time, repeated interactions, gravitational encounters, and environmental effects can leave a galaxy depleted of gas. And without gas, there are no new stars. There's also the possibility that some galaxies simply used up their fuel. During earlier phases, perhaps even during periods of intense activity like the Starburst galaxies we discussed before, a galaxy might have formed stars at such a high rate that it consumed most of its available gas. Once that fuel is gone, the process naturally slows down. What remains is a population of stars that gradually ages. Massive bright stars burn out relatively quickly, ending their lives in supernova explosions. Smaller stars, like our Sun, continue shining for billions of years, but they are less luminous. So over time, a dead galaxy becomes dominated by older, redder stars. Its overall colour shifts, its brightness softens, and its structure becomes more stable, less dynamic. As you sit here, perhaps noticing how the flow of ideas has become a little more gentle, there's something almost reflective about this stage in a galaxy's life. Not dramatic, not intense, but settled. A galaxy that has finished forming new stars isn't empty. It's full of history. Every star within it carries information about the conditions under which it formed. The distribution of those stars, their ages, their compositions, all tell a story about the galaxy's past. In that sense, a dead galaxy is not inactive in a meaningful way. It's complete. Or at least complete in terms of its major phase of growth, and that idea becomes even more intriguing when we look at galaxies in the early universe. Because astronomers have found examples of galaxies that appear to have stopped forming stars surprisingly early, not long after the universe itself began forming structures. One such example is ZF-Cosmos-20115. This galaxy, observed at a time when the universe was only about 1.7 billion years old, shows signs of having already gone quiet. It appears to have formed a large number of stars relatively quickly, and then stopped. Again, this challenges expectations. If galaxies can grow rapidly and then shut down early, It suggests that the processes governing their evolution are more varied than a simple gradual timeline would imply. Some galaxies take their time, others burn through their fuel quickly, some remain active for billions of years, others enter a quiet phase much sooner. And all of these pathways exist within the same universe. There's a kind of balance to it. Activity and stillness, growth and stability, bursts of energy followed by long periods of calm. As we move forward, that balance becomes more apparent. Because the extremes we've explored so far, galaxies that grow too quickly, galaxies that burn intensely, galaxies that stop forming stars, are all part of a larger spectrum. Different ways that matter and energy can organize themselves under the same fundamental laws. Imagine two galaxies drifting toward each other. Not quickly, not with any sense of urgency, but slowly, almost casually, guided only by gravity. At first, there's nothing dramatic about it. From a distance, they might not even seem connected. Just two separate systems, each following its own quiet path through space. But over time, those paths begin to bend. Gravity is subtle like that. It doesn't need sudden force. It works patiently, gradually pulling objects closer together, adjusting their trajectories in ways that only become obvious after long stretches of time. And eventually those two galaxies meet. Not in the way objects collide here on Earth, not with impact and shattering, but in something far more extended, far more complex. A collision that unfolds over hundreds of millions, sometimes billions, of years. A slow-motion transformation. One of the most well-known examples of this process is the pair known as the antennae galaxies. At first glance, they don't look like two separate galaxies anymore. Their structures are stretched, distorted, pulled into long curved streams of stars and gas that extend far beyond their original shapes. Those extended features, the antennae that give them their name, are not decorative. They're the result of gravitational forces pulling material outward as the galaxies pass through each other. Because that's another detail worth pausing on. When galaxies collide, the stars themselves almost never crash into one another. There's simply too much space between them. Instead, what interacts most strongly is the gas. Gas clouds within each galaxy begin to compress as they are pulled and pushed by gravitational forces. Regions that were once stable suddenly collapse, triggering intense bursts of star formation. So even though the collision is slow, the effects can be dramatic. Entire regions light up with new stars. Clusters form, energy spreads through the system, and over time, the original structures of the galaxies begin to dissolve. Their spiral arms stretch and twist, their cores shift, and eventually, after enough time has passed, the two galaxies merge into a single, larger system. That final system often looks very different from either of the original galaxies. Instead of a neat spiral, the result is usually an elliptical galaxy, more rounded, less structured, with stars moving in a wider range of orbits. In a way, the collision erases the previous order and replaces it with something new. But again, this isn't a sudden change. From a human perspective, it's almost impossible to observe directly. What we see instead are snapshots, galaxies at different stages of interaction, each one offering a glimpse into a process that takes far longer than any human lifetime. Some galaxies are just beginning to feel each other's influence, their shapes still mostly intact but slightly distorted. Others are deep into the interaction, with long tidal tails of stars stretching outward, and some have already merged, leaving behind a single galaxy that carries the combined mass and history of both. As you sit here, letting these ideas unfold slowly, there's something almost gentle about the scale of it. Even a collision at this level doesn't involve sudden violence in the way we usually imagine. It's more like a gradual blending, a reshaping that happens over time guided by gravity without any clear beginning or end. Now, there's another example that's a little closer to home. The Milky Way itself is not isolated. It's part of a small group of galaxies, including the Andromeda Galaxy, which is the nearest large galaxy to us, and these two are on a slow path toward each other. Not something to worry about, not something that will happen anytime soon, but something that is already set in motion. In about 4 to 5 billion years, the Milky Way and Andromeda will begin to interact. Their structures will distort, their gas will compress, new waves of star formation will spread through both systems, and eventually, after multiple passes and gradual merging, they will form a single larger galaxy. Sometimes this future system is referred to informally as Milkomeda, a blend of the two names. It's a reminder that galaxy collisions are not rare events. They're a natural part of how galaxies evolve. Given enough time, most large galaxies will experience multiple interactions, each one adding to their mass, altering their structure, shaping their future. And these interactions don't just affect the galaxies themselves, they influence their surroundings. Stars can be thrown into new orbits, sometimes even ejected into intergalactic space. Gas can be redistributed, forming new regions of star formation, or being pushed out entirely. The environment becomes more dynamic, more complex. There's also something interesting about the timing of these events. Collisions often trigger starbursts, those intense periods of star formation we discussed earlier. The gravitational disturbance compresses gas so efficiently that the rate of star formation increases dramatically. So in a way, collisions can act as catalysts. They take relatively stable systems and push them into more active phases. But just like starbursts, this activity doesn't last forever. Eventually, the gas is consumed or dispersed, the rate of star formation declines, and the merged galaxy settles into a new, quieter state. A different structure, a different balance, but still part of the same long process of evolution. As your thoughts continue to slow, maybe becoming a little less focused on exact details and more on the overall picture, it becomes easier to see how these pieces connect. Galaxies that grow through mergers, galaxies that burn brightly during interactions, galaxies that eventually quiet down, each stage feeding into the next. Nothing isolated, nothing fixed, everything changing, just at a pace that stretches far beyond everyday experience. And that's part of what makes these collisions feel different. They're not sudden events, they're extended processes, transformations that unfold so slowly that, from one moment to the next, nothing seems to happen. But over millions and billions of years, everything changes. Structures dissolve and reform, stars shift their paths, new systems emerge, and within those systems, new extremes can appear. Because once galaxies begin interacting, once their gas and stars are redistributed, the conditions for unusual behavior become more likely. Higher densities in some regions, lower densities in others, energy flowing in new ways. Light, on its own, feels simple. You turn on a lamp and a room brightens. You look up at the night sky, and a few stars stand out against the darkness. Even the sun, as overwhelming as it is, becomes something you can grow used to, something your eyes adjust to over time. But when it comes to galaxies, brightness is not just a matter of illumination, it becomes something else entirely. Because there are galaxies in the universe that don't just shine, they dominate, they pour out so much energy that the idea of brightness stops feeling like a gentle increase and starts to feel like a category of its own. And the interesting part is that, in many of these cases, the light isn't coming from the stars alone. It's coming from something deeper, something more concentrated. To ease into this, it helps to remember how a typical galaxy shines. In something like the Milky Way, the overall brightness is the combined light of hundreds of billions of stars. Each one contributes a small amount, and together they create the soft glow we associate with a galaxy. It's distributed, spread out, balanced. Even in active galaxies, where star formation is intense, the light is still coming from many different regions at once. But in the brightest galaxies in the universe, that balance shifts. Instead of being spread evenly, the energy becomes concentrated in a much smaller region. and that changes everything. Because once energy is concentrated, it can reach levels that seem almost disproportionate to the size of the system. One of the most well-known examples of this is 3C273. At first glance, 3C273 doesn't even look like a galaxy in a telescope. It appears more like a bright point of light, almost star-like. In fact, when it was first observed, astronomers weren't entirely sure what they were looking at. But that point of light is not a single star. It's the extremely bright core of a distant galaxy, a quasar. Quasars are among the most luminous objects in the universe, powered by supermassive black holes at the centers of galaxies. As matter falls toward the black hole, it forms an accretion disk, a swirling, rapidly spinning structure of gas and dust. Friction and gravitational forces heat this material to incredibly high temperatures, causing it to emit enormous amounts of energy. In some cases, that energy output can exceed the total light of the entire galaxy surrounding it. So instead of the galaxy being the main source of brightness, the central region becomes the dominant feature. 3C273 is one of the closest and brightest quasars we know, and it's visible across billions of light years. That means the light we see today began its journey long before Earth even existed in its current form. And yet, even at that distance, it stands out. That alone gives you a sense of just how much energy is being released. Now, 3C273 is just one example. There are quasars that are even more luminous, pushing the limits of what we thought possible. Take TON 618. This object is not just bright. It's extreme in multiple ways. At its center lies one of the most massive black holes ever discovered, with a mass estimated at tens of billions of times that of the Sun. The energy produced as material falls into this black hole is so intense that TON 618 outshines entire galaxies by a significant margin. And again, what we're seeing is not the galaxy as a whole, it's the core, a relatively small region, on cosmic scales, producing an extraordinary amount of light. But not all of the brightest galaxies rely on quasars. Some achieve their luminosity through different means. There are galaxies known as ultra-luminous infrared galaxies, or ULIRGs, which shine intensely in the infrared part of the spectrum. One example is ARP 220. ARP 220 is the result of a merger between two galaxies, similar to the interactions we discussed earlier. That merger has triggered an enormous burst of star formation, along with the accumulation of large amounts of dust. The dust absorbs visible light from the newly formed stars and re-emits it as infrared radiation. So while ARP 220 might not appear exceptionally bright in visible light, in the infrared it becomes one of the most luminous galaxies known. In a way, it's hiding its brightness. The energy is still there, but it's being released in a different form. And that's another reminder that brightness depends on how you measure it. Visible light is only one part of the electromagnetic spectrum. There's also infrared, ultraviolet, X-rays, radio waves. A galaxy might appear dim in one range and extremely bright in another. So when astronomers talk about the brightest galaxies, they're often referring to total energy output across all wavelengths. And in that sense, objects like quasars and ultra-luminous infrared galaxies dominate. Now, there's something else worth noticing here. All of these extreme cases involve concentration. In quasars, energy is concentrated around a central black hole. In ULIRGs, star formation is concentrated in dense, dusty regions. In both cases, the key factor is not just how much energy is produced, but how tightly it's packed. Because when energy is concentrated, it becomes more noticeable, more intense, more capable of standing out across vast distances. As you listen, perhaps feeling a bit more settled into the flow of these ideas, there's something almost consistent about this pattern. Extremes often come from concentration, whether it's mass, energy, or activity. When something that is usually spread out becomes focused, the result becomes more dramatic. And that pattern shows up again and again in the universe. Now consider the implications of this. If a galaxy's brightness can be dominated by a relatively small central region, then what we see when we observe distant galaxies might not always reflect the entire system. We might be seeing just the brightest part, the most active region, while the rest remains less visible, less prominent. In some cases, entire galaxies are detected primarily because of their active cores. Without that activity, they might be much harder to observe, which means that our view of the universe is in part shaped by what stands out, by what shines the most, and that introduces a subtle bias. We are more likely to notice the brightest galaxies, the most extreme cases, simply because they are easier to detect across great distances. Meanwhile, quieter galaxies, more typical ones, might remain less visible, especially in the early universe. So the brightest galaxies are not just interesting in themselves, they also influence how we perceive the larger picture. They act as beacons, visible across billions of light years, helping us trace the structure of the universe at large scales. They mark regions of intense activity, regions where matter is concentrated, where processes are happening at extraordinary rates, and by studying them, astronomers can learn about the environments in which they exist, the conditions that allow such extreme luminosity to develop, the interactions, the flows of gas, the presence of massive black holes. All of these pieces come together in these systems. As your thoughts continue to slow, becoming a little less focused on individual details and more on the overall pattern, it becomes easier to see how this fits into the broader story. Galaxies that grow too quickly, galaxies that burn intensely, galaxies that shine with extraordinary brightness. Each one represents a different way of reaching an extreme, and each one adds to our understanding of what's possible. Hidden within the calm glow of many galaxies, there is something that doesn't glow at all. It doesn't shine, it doesn't reflect, and it doesn't announce itself directly. And yet, in many of the most extreme galaxies we've explored, it turns out to be the main reason those galaxies behave the way they do. At the very centre, often buried beneath layers of stars, gas and dust, sits a black hole. Not the kind you might casually imagine, not the small remnants of collapsed stars, but something much larger. Something that doesn't just belong to the galaxy. Something that shapes it. These are supermassive black holes, and once you begin to notice them, they appear almost everywhere. In fact, the Milky Way itself has one, quietly sitting at its centre. It's called Sagittarius A star, and while it is enormous by everyday standards, containing about 4 million times the mass of the Sun, it is actually quite modest compared to what we're about to look at. Because in some galaxies, the central black hole is not just large, it is overwhelmingly large. And that difference changes everything. To ease into this idea, it helps to consider how a black hole grows. A black hole increases in mass by pulling in material from its surroundings. Gas, dust, even stars can drift too close and become captured by its gravity. As this material falls inward, it doesn't simply disappear quietly. It forms a disk, heating up and releasing energy, sometimes becoming the brightest region in the entire galaxy, as we saw with quasars. Over time, this process can continue, especially in galaxies that have experienced mergers. When two galaxies collide, their central black holes can eventually merge as well, creating an even larger black hole. So just like galaxies themselves, black holes can grow through accumulation, and in the largest galaxies, especially those at the centres of clusters, this process can continue for billions of years. The result is something that stretches the limits of scale once again. One of the most striking examples is the black hole at the centre of Messier 87, often referred to simply as 87 asterisk. This black hole has a mass of about 6.5 billion times that of the Sun. It's so large that in 2019, it became the first black hole ever directly imaged by the Event Horizon Telescope collaboration. That image, a faint ring of light surrounding a dark centre, gave us our first direct glimpse of something that had previously only been inferred through indirect evidence. And what it showed was not just a black hole, it showed the influence of something that dominates its surroundings. The gravity of M87 star is so strong that it shapes the motion of stars and gas across a significant portion of the galaxy's central region. It also drives powerful jets of energy, streams of particles moving at nearly the speed of light, extending thousands of light years into space. These jets don't just look impressive, they affect the galaxy itself. They heat surrounding gas, prevent it from cooling, and in doing so influence whether new stars can form. So the black hole is not just sitting at the centre, it's actively participating in the evolution of the galaxy. Now, M87 star is enormous, but it's not the largest known. There are black holes that go even further. One of the most extreme examples is found in the quasar TON 618, which we touched on earlier. The black hole at the centre of TON 618 is estimated to have a mass of around 66 billion times that of the Sun. That number is difficult to process, but what it means in practical terms is that this black hole dominates its environment to an extraordinary degree. The region around it becomes intensely luminous as material falls inward, producing energy that outshines entire galaxies. And yet, the black hole itself remains invisible. Only its effects are seen, and that pattern, the presence of something unseen shaping everything around it, is one we've encountered before. Dark matter, ultra-diffuse galaxies, faint structures. But here, the scale is different, more concentrated, more immediate, because while dark matter halos extend across galaxies, these black holes sit at a single point, exerting influence from the centre outward. As you listen, perhaps feeling a little more settled into this slow unfolding of ideas, there's something almost grounding about that contrast. Vast diffuse structures on one hand, dense concentrated points on the other, both essential, both shaping the same systems. Now there's an interesting relationship that astronomers have noticed. The mass of a galaxy's central black hole often correlates with the properties of the galaxy itself, particularly the mass of its central bulge. This suggests that the growth of the black hole and the growth of the galaxy are linked. Not independent processes, but interconnected ones. As the galaxy evolves, so does the black hole. As the black hole grows, it influences the galaxy. It's a feedback loop. Material flows inward, feeding the black hole. Energy flows outward, affecting the galaxy. And over time, a kind of balance can emerge. But in extreme cases, that balance can tip. The black hole can become so massive, so active, that its influence dominates the system. It can regulate star formation, drive outflows, reshape the distribution of gas. In a sense, it becomes the central engine of the galaxy. And that idea changes how you think about galaxies as a whole. They're not just collections of stars, they're systems, organised around something much more concentrated, something that doesn't emit light directly, but controls how light is produced. Now there's another aspect to consider: time. Black holes don't grow quickly in human terms, but over billions of years, even small differences in growth rate can lead to enormous variations in mass. Some galaxies, especially those that have undergone many mergers, provide more opportunities for black holes to grow, more material, more interactions, more accumulation. Others remain quieter, with smaller central black holes. So just as galaxies can follow different evolutionary paths, so can their central black holes. And in the most extreme cases, those paths lead to objects that are difficult to fully comprehend, not just because of their size, but because of their influence. As your thoughts continue to drift, becoming a little less focused on precise numbers and more on the overall picture, it becomes easier to see how this fits into the broader pattern. Extremes in size, extremes in brightness, extremes in activity, and now extremes in concentration, each one revealing a different aspect of how the universe organises itself, and each one connected to the others. Because the brightest galaxies often host the largest black holes, the most active galaxies are often shaped by what happens at their centres. And even the quiet, dead galaxies we discussed earlier can owe their stillness, at least in part, to the influence of a central black hole that has altered their ability to form new stars. So nothing here exists in isolation. Every extreme has roots in multiple processes, interacting over long periods of time, and once you begin to follow those connections, the picture becomes richer, more layered, more complete. Gravity, for the most part, feels predictable. You drop something, and it falls. You step forward, and your feet stay grounded. Even when we think about planets orbiting stars or stars orbiting the centers of galaxies, the motion still follows a pattern that feels steady, almost reassuring. But there is a deeper layer to gravity, one that doesn't just pull on objects, it changes the space those objects move through. And once that idea begins to settle in, slowly, without needing to force it into a clear picture, something else follows. Light itself can be bent. Not metaphorically, not as a trick of perception, but physically, measurably, in ways that reshape what we see. This is where galaxies begin to do something very unusual. They don't just shine, they act like lenses. To ease into this, it helps to take a small step back. When light travels through empty space, it moves in straight lines. That's the simplest case, the one our intuition is built around. But space, as described by Albert Einstein in his theory of general relativity, is not always empty in the sense we imagine. Massive objects, like galaxies, don't just sit within space, they curve it. And when space curves, the paths that light takes also curve. So if light from a distant galaxy passes near another massive galaxy, on its way toward us, its path can be bent. Sometimes slightly, sometimes dramatically. And when that happens, the image we see is no longer a simple, direct view. It becomes distorted, stretched, sometimes even multiplied. One of the most striking examples of this effect is known as the Einstein cross. At first glance, it looks almost symmetrical, 4 bright points arranged around a central galaxy. But those 4 points are not separate objects. They are multiple images of the same distant quasar, its light bent and split as it passes around a foreground galaxy. So what you're seeing is not just one object, but one object appearing in several places at once, not because it moved, but because the light took different paths through curved space. That alone is enough to feel a little unusual, but there are even more extreme cases. Consider the Abell 2218. This is not just a single galaxy, but a massive cluster, containing many galaxies bound together by gravity. The total mass of the cluster is so large that it creates a very strong gravitational lens. When astronomers observe Abell 2218, they see arcs of light, long curved streaks that wrap around the cluster. Those arcs are not objects shaped that way. They are distant galaxies, their light stretched and distorted as it passes through the curved space created by the cluster's mass. In some cases, the distortion is so strong that it produces rings, nearly complete circles of light surrounding the central mass. These are called Einstein rings, and they occur when the alignment between the observer, the lensing galaxy, and the background object is just right. It's a delicate arrangement, but when it happens, the result is something that looks almost designed, as if the universe briefly arranged itself into a perfect circle of light. Now, there's something else happening here, something a bit more subtle. When light is bent by gravity, it doesn't just change direction. It can also take different amounts of time to reach us. This means that when we see multiple images of the same object through gravitational lensing, those images can represent slightly different moments in time. One path might be shorter, another longer. The light travelling along each path arrives at a different moment. So in a very real sense, a single observation can contain multiple versions of the same object, each one from a slightly different point in its history. That's where the idea of galaxies bending not just light but time begins to take shape, not in a way that allows travel or reversal, but in a way that affects how events are observed. You're not just seeing where something is, you're seeing when it was, from more than one perspective at once. As you listen, perhaps noticing how the ideas have become a little more layered, a little more interconnected, there's something quietly fascinating about that. Because it means that the universe doesn't just present itself directly. It filters itself, shapes itself, through the structures within it. Galaxies, clusters, dark matter, all contributing to how light moves, and therefore how we perceive everything else. There's also a practical side to this. Gravitational lensing isn't just an odd effect, it's a tool. Astronomers use it to study objects that would otherwise be too faint or too distant to observe. A massive galaxy or cluster can act like a natural telescope, magnifying the light from objects behind it. This has allowed scientists to detect galaxies from the very early universe, galaxies that formed not long after the Big Bang, by using intervening mass to amplify their light. In that sense, the universe helps us observe itself. Structures that form later make it possible to see structures that formed earlier. Everything connected through the same underlying physics. There's another layer as well. Because gravitational lensing depends on mass, including mass we cannot see, it provides one of the strongest pieces of evidence for dark matter. When astronomers map how light is bent around a galaxy cluster, they can infer how mass is distributed within that cluster. And often, the distribution doesn't match the visible matter alone. There is more mass present than can be accounted for by stars and gas. Again, something unseen is shaping what we observe. So gravitational lensing doesn't just reveal distant galaxies, it reveals the invisible structure of the universe itself. Now, if you take a moment to let all of that settle, there's something almost quiet about it. Not in the sense that it's simple, but in the sense that it unfolds naturally from the same principles we've been following. Mass shapes space, space guides light, light carries information, and by following that chain step by step we begin to understand how galaxies can influence not just their own structure, but the appearance of everything beyond them. They become more than objects, they become intermediaries, shaping the path of light across vast distances. And once you start to think of galaxies in that way, not just as collections of stars, but as structures that influence the very geometry of space, the idea of extreme begins to shift again. It's no longer just about size or brightness, it's about effect, about how far the influence of something extends, and in this case, that influence reaches far beyond the galaxy itself. It extends into the paths of photons travelling for billions of years. It reaches into how we see the universe at its larger scales. Speed at first feels like something we understand. A car accelerates, a plane lifts off, a train moves steadily along its tracks. Even when those speeds become high, they remain within a range the mind can still follow. You can imagine what it means to go faster, to cover more distance in less time. But once you step into the scale of galaxies, that sense of speed begins to stretch in a different way. Because galaxies don't just sit quietly in space, they rotate. Every star, every cloud of gas, every particle of dust is in motion, orbiting the centre under the influence of gravity. And just like everything else we've explored, this motion follows patterns that seem calm at first glance, until you look more closely. In a system like the Milky Way, stars orbit the centre at speeds of roughly 200 to 250 kilometers per second. That's already fast enough to circle the entire Earth in a matter of minutes, yet within the galaxy, it feels steady, balanced. The key is scale. The distances are so vast that even at those speeds it takes hundreds of millions of years for a single orbit to complete. So the motion becomes gentle when viewed over time, almost like a slow drift rather than a rush. But not all galaxies follow that calm rhythm. Some spin faster, much faster, and when they do, the balance between gravity and motion becomes something more delicate. Because rotation is not just movement, it's tension. Stars moving outward due to their velocity, held inward by gravity. If the speed becomes too high, the galaxy risks losing its structure. If gravity is too strong, the motion becomes more compressed. So when astronomers find galaxies that rotate at extreme speeds, it raises an important question. How do they hold together? One of the most well-known examples is UGC 12591. At first glance, it doesn't look radically different from other spiral galaxies. It has a disk, a central region, a familiar shape. But when astronomers measured how fast its stars are moving, they found something remarkable. The rotation speed of UGC 12,591 is estimated to be around 500 kilometers per second. That's roughly twice the rotational speed of the Milky Way. And that difference matters, because doubling the speed doesn't just double the effect, it increases the outward force significantly, meaning that the galaxy must have enough gravitational pull to keep everything bound despite that motion. Which brings us back to something we've encountered before: mass. For a galaxy to spin that quickly without flying apart, it must be extremely massive. Not just in terms of visible stars, but in total mass, including dark matter. In fact, galaxies like UGC 12591 are believed to contain enormous dark matter halos, providing the additional gravitational pull needed to counteract their high rotational speeds. So once again, something invisible plays a crucial role. But there's another layer to this. Rotation speed isn't just about how fast a galaxy spins. It also tells us something about how matter is distributed within it. In many galaxies, rotation curves, the way speed changes with distance from the centre, reveal the presence of dark matter because the speeds don't drop off as expected. In fast-spinning galaxies, those curves often remain flat or even elevated across large distances, indicating that the mass is spread out in a way that continues to influence motion far from the centre. And that distribution is not always intuitive. You might expect most of the mass to be concentrated in the central region, but the behaviour of these galaxies suggests that the outer regions are also heavily influenced by unseen mass. As you sit here, perhaps noticing the steady pace of these ideas, there's something quietly consistent about this pattern. Whenever something reaches an extreme, whether it's size, brightness, or speed, there's often an underlying structure supporting it. Something that allows the system to exist without breaking apart. In this case, that structure is gravity, extended and reinforced by dark matter. Now there's an interesting contrast to consider. In smaller systems, extreme speeds often lead to instability. Objects move too fast, forces become unbalanced, and the system changes rapidly. But in galaxies, because of their scale, even extreme speeds can be sustained over long periods. The motion is continuous, but the timescale is so large that everything still appears stable. It's a different kind of balance, one where opposing forces, motion outward and gravity inward, remain in equilibrium over billions of years. There are also galaxies that push this balance in more subtle ways. Not necessarily the fastest in absolute terms, but structured in ways that emphasize rotation. Thin disk galaxies, for example, where most of the mass is concentrated in a narrow plane, can exhibit very organized rotational motion. In these systems, stars move in relatively coherent orbits, creating a sense of order that contrasts with the more random motion seen in elliptical galaxies. And when that organized motion reaches high speeds, the result is something that feels almost precise, not chaotic, not turbulent, but finely balanced. It's also worth noting that rotation plays a role in shaping the galaxy itself. The faster a galaxy spins, the more it tends to flatten into a disk. Centrifugal effects, balanced by gravity, distribute material outward, creating the familiar spiral structures we often associate with galaxies. So in a way, speed contributes to form. The shape of a galaxy is partly a reflection of how it moves. Now take a moment to let that idea settle. A galaxy is not just a collection of stars. It's a dynamic system, constantly in motion, its structure shaped by the interplay of forces acting over immense periods of time. And when that motion becomes extreme, it reveals something about the limits of those forces. How fast can a galaxy spin before it loses stability? How much mass is required to sustain that motion? What role does dark matter play in maintaining the balance? These are questions that astronomers continue to explore, because each extreme case provides a new data point, a new way of testing our understanding of how galaxies work. As your thoughts continue to drift, perhaps becoming less focused on exact numbers and more on the broader picture, it becomes easier to see how this fits into everything we've discussed. Galaxies that grow too large, galaxies that form stars too quickly, galaxies that shine too brightly, galaxies that rotate too fast, each one pushing a different aspect of the system to its limit, and each one revealing something about the underlying rules. Structure, for the most part, gives us comfort. When something has a clear shape, a pattern, a recognizable form, it becomes easier to understand. Spiral arms curve in predictable ways, elliptical galaxies glow with smooth symmetry, and even the extremes we've explored so far still tend to follow some kind of internal logic. But not everything in the universe settles into that kind of order. Some galaxies don't form neat spirals, they don't smooth themselves into ellipses, they don't present a clear outline that the eye can follow from one edge to the other. Instead, they appear scattered, uneven, almost unfinished. These are irregular galaxies, systems that don't fit into the standard categories, and in many cases they represent a different kind of extreme, not because they are the largest, or the brightest, or the fastest, but because they lack the structure we expect. One of the most familiar examples is the Large Magellanic Cloud. This galaxy orbits the Milky Way, making it one of our closest galactic neighbours. Unlike a spiral galaxy, it doesn't have well-defined arms. Its stars and gas are distributed in a more uneven way, with bright regions of star formation scattered throughout. There is a central bar-like structure, but beyond that, the overall shape feels loose, almost as if it hasn't fully settled into a stable configuration. Nearby, there's another example, the Small Magellanic Cloud. Even more irregular in appearance, this galaxy looks like a diffuse collection of stars and gas, with no obvious symmetry. It's interacting not only with the Milky Way, but also with the Large Magellanic Cloud, and those interactions contribute to its uneven structure. Gravitational forces pull and distort, stretching material, redistributing gas, creating regions of activity that don't align into a simple pattern, and that's one of the key reasons galaxies lose their shape: interaction. When galaxies pass near each other, or collide, or simply exist within a strong gravitational environment, their structures can be disrupted. The neat spirals become stretched, the smooth ellipses become uneven, and what remains is something more chaotic. Another well-known example of this kind of disruption is the IC10. IC10 is a starburst irregular galaxy, meaning that not only does it lack a clear structure, but it's also actively forming stars at a high rate. Its appearance reflects that activity, with bright scattered regions where new stars are being born, surrounded by more diffuse areas of gas and older stars. There's no single pattern to follow, no simple geometry, just a collection of processes happening at different locations, each contributing to the overall form. And then there are galaxies like NGC 4449. This one is particularly interesting because it shows signs of past interactions, with streams of stars extending outward, hints of tidal forces reshaping its structure. It's not just irregular in a static sense, it's irregular because it has been, and perhaps still is, in the process of changing. Its current shape is a snapshot of that process, a moment in a longer transformation. As you sit here, letting these ideas unfold at a steady pace, there's something quietly different about this kind of extreme. It's not about pushing a single parameter to its limit, it's about the absence of order, the lack of a clear pattern, and that can be just as informative. Because when a galaxy doesn't follow the usual rules of structure, it often reveals something about its history. Perhaps it has undergone recent interactions. Perhaps it's still forming. Perhaps it hasn't had enough time or the right conditions to settle into a more stable configuration. Irregular galaxies are often rich in gas. That's another important detail. Gas is the raw material for star formation, and when it's distributed unevenly, it can lead to bursts of activity in different regions. Instead of a smooth, organised process, star formation becomes patchy, localised, and sometimes intense. This ties back to something we explored earlier, starburst galaxies. Many irregular galaxies are also starburst galaxies, because the same processes that disrupt structure, gravitational interactions, turbulence, gas compression, also trigger rapid star formation. So the lack of shape is not just a visual characteristic, it's connected to how the galaxy behaves, how it evolves, how it forms stars. There's also a more subtle aspect to consider. In the early universe, many galaxies were likely irregular. Before structures had time to settle, before repeated rotations smoothed things out, galaxies may have started as more chaotic systems. Over time, as gravity shaped their motion and redistributed material, some of them developed into the more familiar spiral or elliptical forms. So irregular galaxies might represent an earlier stage of evolution, or in some cases a system that has been pushed back into that state by interactions. Either way, they remind us that order is not guaranteed. It's something that emerges under certain conditions, but it can also be disrupted. As your thoughts continue to slow, becoming a little less concerned with precise classifications and more open to the overall picture, it becomes easier to accept that not everything needs to fit into a neat category. Some galaxies are structured, some are not. Some evolve into order, some remain in a more chaotic state. And all of these variations exist within the same universe, governed by the same underlying laws. That's part of what makes this exploration feel consistent, even as the details change. There's always a pattern at deeper level, even when the surface appears irregular. Now, consider how this connects to everything we've seen so far. Galaxies that grow too large, galaxies that form stars too quickly, galaxies that shine intensely, galaxies that spin rapidly, and now galaxies that don't settle into a clear shape at all. Each one represents a different way in which the usual expectations are stretched or broken, and each one adds another layer to our understanding. Long before any galaxy settled into a familiar shape, before spiral arms had time to wind into graceful curves or massive ellipticals gathered the remnants of countless mergers, there was a time when galaxies were only just beginning, not fully formed, not stable, but already present. And the remarkable part is that we can still see them, not as they are now, but as they were when the universe itself was young. To understand how that's possible, it helps to return to something we've touched on before, but to look at it a little more slowly. Light takes time to travel. That's a simple idea, but its consequences are far-reaching. When you look at something far away, you're not seeing it as it is in this moment. You're seeing it as it was when the light left it. A nearby star might appear as it was a few years ago. A distant galaxy might appear as it was millions or billions of years ago. And when astronomers push their observations to the limit, using powerful instruments like the James Webb Space Telescope, they begin to see galaxies whose light has been travelling for more than 13 billion years. That means we are looking back to a time when the universe was only a small fraction of its current age. Less than 1 billion years old, in some cases even earlier. These are among the oldest galaxies we can still detect, and they don't look quite like the galaxies we're used to. One of the most well-known examples is GN-Z11, which we encountered earlier. Its light comes from a time when the universe was only about 400 million years old. That's not long after the Big Bang, at least on cosmic timescales. And yet, GN-Z11 is already a galaxy. It has stars, it has structure, it's actively forming new stars, which is remarkable because it suggests that galaxy formation began very early and in some cases proceeded more quickly than we might expect. But GN-Z11 is only one example. More recently, observations from the James Webb Space Telescope have revealed even earlier candidates. One of them is JADES-GS-Z 13-0, a system that may date back to a time when the universe was just a few 100 million years old. At that stage, the universe was still transitioning from a very different state. After the Big Bang, there was a period often referred to as the Cosmic Dark Ages, when the universe was filled mostly with neutral hydrogen gas and had not yet formed many luminous objects. Gradually the first stars ignited, then small galaxies began to assemble, and as more stars formed, their radiation began to ionize the surrounding gas, making the universe more transparent to light. This process is known as rionization. The galaxies we're talking about now existed during or just after that period. They were among the first sources of light to emerge from the darkness, and that gives them a special role. They are not just old, they are foundational. They represent the early steps in the formation of everything that came later. Now there's something important to keep in mind. When we say oldest galaxies we can see, we don't mean that these galaxies are necessarily the oldest that ever existed. We mean that they are the oldest whose light has reached us, and that we have been able to detect with current technology. There may have been earlier galaxies, smaller, fainter, less developed, whose light is too dim or too redshifted for us to observe. So what we're seeing is a boundary, the edge of our observational reach. As telescopes improve, that edge moves. We see further back, we detect fainter objects, and the picture becomes more complete. As you sit here, perhaps noticing how your thoughts have become a little more spacious, there's something quietly fascinating about that idea, because it means that our understanding of the early universe is not fixed. It's expanding, just like the universe itself. Each new observation adds another piece, another hint of what those early galaxies were like. Now consider what those galaxies must have experienced. The early universe was denser, hotter, more uniform in some ways, but also full of small fluctuations, regions where matter was slightly more concentrated. Those fluctuations were the seeds of structure. Gravity amplified them over time, pulling matter together, forming the first stars and galaxies. But the conditions were not the same as they are today. Gas was more abundant, interactions between galaxies were more frequent, everything was closer together. So the processes that shaped early galaxies may have been more intense, more rapid, which helps explain why some of these early systems appear more developed than expected. Still, even with that context, there's something surprising about their existence. Because when astronomers first began to detect these distant galaxies, they expected to see small, faint, irregular systems, not fully formed, not yet organized. But in many cases, what they found were galaxies that already showed signs of significant structure and activity. Not identical to modern galaxies, but not as primitive as expected either. And that suggests that galaxy formation began earlier and progressed more quickly than some models predicted. As your mind continues to settle, becoming less focused on exact timelines and more open to the overall flow, it becomes easier to see how this connects to everything else we've explored. Galaxies that grow too fast, galaxies that form stars intensely, galaxies that evolve quickly. All of these ideas come together when we look at the earlier systems, because the early universe was a place where extremes were more common, where conditions allowed for rapid change, where structures could emerge quickly. Now there's another layer to this. When we observe these distant galaxies, we're not just learning about them, we're learning about the universe itself, the distribution of matter, the rate of expansion, the processes that govern the transition from a simple, uniform state to the complex structure we see today. Each galaxy acts like a marker, a point in time, a piece of evidence. And by studying many of them, astronomers can begin to reconstruct the history of the universe, not in a single, continuous view, but in fragments, snapshots from different moments, assembled into a larger picture. There's something almost reflective about that, because it mirrors the way memory works. We don't experience the past directly. We reconstruct it from pieces, from traces, from the information that remains. In a similar way, the universe leaves behind light, signals, clues, and we use those to understand what came before. As we move forward, that idea becomes even more interesting, because not all early galaxies behave the same way. Some follow expected patterns, others do not. Some appear too large, too bright, too structured for their age. And those cases raise new questions, not just about how galaxies form, but about how quickly they can reach certain stages of development. Something about the early universe used to feel orderly. Not in the sense that everything was calm, because it wasn't. It was dense, energetic, constantly changing. But there was still a kind of expectation about how things should unfold. First, small structures, then gradual growth, then, much later, the large complex galaxies we see today. That sequence made sense. It followed naturally from the idea that gravity needs time to gather matter, that stars take time to form, that galaxies assemble piece by piece over billions of years. And for a long time, that picture held together reasonably well, until observations began to reach further back. Because once astronomers started looking deeper into space, and therefore further into the past, something subtle began to shift. The galaxies they were finding didn't always match the timeline. Some of them appeared too developed, too large, too structured, as if they had skipped steps or moved through them much faster than expected. To understand why that matters, it helps to pause for a moment and consider what early actually means in this context. When we observe galaxies that are billions of light years away, we're seeing them as they were billions of years ago. When we push that distance even further, we reach a point where the universe itself was very young. A few 100 million years old. Perhaps 1 billion at most. At that stage, according to earlier models, galaxies should still be in their early phases of formation. Small, irregular, actively assembling, not yet settled into large massive systems. And yet, that's not always what we see. One of the most striking examples comes from recent observations using the James Webb Space Telescope. Among its many discoveries are galaxies like JADES-GS-Z14-0. The name, again, is quiet and technical, but the implications are not. This object appears to exist at a time when the universe was only around 300 million years old, and yet it shows signs of being more massive and more luminous than expected for that epoch. Not just present, but already significant, and it's not alone. There are several similar candidates, galaxies that seem to have formed large numbers of stars very quickly, reaching a level of development that challenges earlier expectations. Now, it's important to approach this carefully. Observing such distant objects is not simple. The light is faint, stretched by the expansion of the universe, and often requires careful interpretation. Measurements of distance, mass, and brightness come with uncertainties. But even with those uncertainties, the pattern remains. There are galaxies that appear to have formed too early, and that raises a quiet but persistent question. How? Because if the timeline we've been using doesn't fully account for these observations, then something needs to be adjusted. Not necessarily replaced entirely, but refined, expanded. One possibility is that galaxy formation in the early universe was more efficient than we thought. In a denser environment, with more gas available and stronger gravitational interactions, matter could have collapsed more quickly, leading to faster star formation and more rapid growth. Another idea is that the initial fluctuations in matter distribution, the tiny variations in density that existed after the Big Bang, may have been more pronounced in certain regions. If some areas started with a higher concentration of matter, they could have formed galaxies earlier and more rapidly than others. There's also the possibility that we are underestimating how quickly stars can form under the right conditions, if gas clouds collapse more efficiently, or if feedback processes like energy from young stars behave differently in the early universe, then the entire timeline of galaxy evolution might need to be reconsidered. As you listen, perhaps noticing how these ideas are unfolding a little more slowly now, there's something almost reassuring about this kind of uncertainty. Not because it makes things simpler, but because it shows that our understanding is still growing. Science doesn't rely on everything being settled. It progresses by encountering things that don't quite fit. And these early galaxies are exactly that. They don't break the rules entirely, but they stretch them. They show us that the universe is capable of moving faster, of assembling structure more quickly than we once assumed. There's another layer to this as well, because when galaxies form early, they influence everything that comes after. Early galaxies produce stars. Those stars create heavier elements. Those elements become part of later generations of stars and planets. So if galaxies are forming earlier than expected, then the entire chain of cosmic evolution might begin earlier as well. More stars, more elements, more complexity, all starting sooner, and that has implications not just for galaxies, but for the history of the universe as a whole. Now, consider how this connects to what we've already explored. Galaxies that grow too large, galaxies that form stars too quickly, galaxies that shine intensely. All of these can be part of the same story. If a galaxy forms early and grows rapidly, it might also experience intense star formation. It might become very bright. It might evolve into one of the extreme systems we've already discussed. So these early forming galaxies are not isolated anomalies. They are part of a broader pattern, a different pathway through the same physical processes. As your thoughts continue to drift, becoming a little less tied to exact numbers and more open to the overall flow, it becomes easier to accept that the universe doesn't follow a single script. There are variations, different starting conditions, different environments, different outcomes, and sometimes those variations lead to results that feel surprising, not because they are impossible, but because they reveal possibilities we hadn't fully considered. There's also something quietly humbling about this, because it reminds us that even when we think we understand the general outline of how things work, there are always details waiting to be discovered, always exceptions that lead to deeper insights, always new observations that refine the picture. Far away from clusters, beyond the crowded regions where galaxies gather and interact, there are places in the universe where almost nothing happens. Not in a dramatic sense, not in a way that announces itself with brightness or motion, but in a quiet, persistent absence. These regions are known as cosmic voids. They are vast, stretching across tens or even hundreds of millions of light years, and within them, galaxies are rare. Not completely absent, but scattered so sparsely that the distance between them becomes almost difficult to imagine. And yet, even in these emptiest parts of the universe, some galaxies exist, alone. To understand what makes these galaxies unusual, it helps to recall something we've seen repeatedly so far. Most galaxies do not live in isolation. They are part of groups, clusters, or larger structures connected by filaments of matter, forming what astronomers call the cosmic web. Gravity pulls them together, interactions shape their evolution, and over time they influence one another in subtle and not so subtle ways. Collisions happen, mergers occur, gas flows between systems. Even when galaxies are not directly interacting, they still exist within environments that affect how they evolve. But in a void, that context changes. The gravitational pull from nearby structures is weaker. Interactions are rare. The galaxy exists for long periods of time without significant external influence. One of the most well-known examples of such isolation is MCG plus 01-02-015. This galaxy is often described as one of the loneliest known. It sits deep within a cosmic void, so far from other galaxies that, for billions of years, it has likely had little to no interaction with its surroundings. If you were somehow inside that galaxy, looking outward, the night sky would feel very different. There would be stars, of course, but beyond the boundaries of the galaxy itself, the vast majority of the sky would be empty. No nearby galaxies shining as distant smudges of light. No dense clusters. Just darkness, stretching in all directions. That kind of isolation is difficult to relate to because on smaller scales, even in remote areas, there are always connections, always interactions. But on cosmic scales, distance can create true solitude. Now, there's something interesting about galaxies like MCG plus 01-02-015. Because without interactions, many of the processes we've discussed simply don't happen. No mergers, no tidal distortions, no bursts of star formation triggered by collisions. Instead, the galaxy evolves more slowly, more gently. Star formation may continue at a steady rate, as long as gas is available. The structure remains relatively undisturbed. There is less external pressure to change. In a way, these galaxies represent a kind of baseline. What happens when a galaxy is left alone? But even that simplicity comes with its own questions, because interactions are not just disruptive, they're also constructive. Mergers can lead to growth, collisions can trigger star formation, environmental effects can shape galaxies into new forms. So without those influences, how does a galaxy evolve? Does it remain small? Does it continue forming stars longer, since its gas is not being stripped away? Does it develop differently from galaxies and clusters? These are questions that astronomers continue to explore, because isolated galaxies provide a kind of natural experiment, a way to observe what happens when certain variables are removed. As you sit here, perhaps noticing the calmness of this idea, there's something almost fitting about these galaxies. They are not extreme in the way we've seen before, not the brightest, not the fastest, not the most massive, but they are extreme in a different sense. They are defined by absence, by distance, by the lack of interaction. And that absence shapes everything about them. There's also a broader context to consider. Cosmic voids themselves are part of the large-scale structure of the universe. Matter is not distributed evenly. Instead, it forms a network of filaments and clusters, with vast empty regions in between. Galaxies form along the filaments, where matter is more concentrated. Voids are the spaces left behind, and over time, as the universe expands, these voids can grow larger. Matter moves toward denser regions, leaving the emptiest areas even more sparse. So galaxies within voids may become even more isolated as time goes on. Their already distant neighbours move further away. Their environment becomes even quieter. There's something almost reflective about that, because it shows how the same process, the expansion of the universe, can lead to very different outcomes depending on location. In dense regions, galaxies interact more frequently. In voids, they drift apart. Two different experiences of the same underlying expansion. Now consider how this connects to everything we've explored so far. Galaxies that collide and merge. Galaxies that trigger bursts of star formation. Galaxies shaped by their environments. And then, galaxies that are largely untouched by those influences. Each one represents a different path, a different way for matter and energy to organize over time. As your thoughts continue to settle, becoming a little more spacious, it becomes easier to see how these variations fit together. The universe is not uniform in its behavior. It allows for extremes in many directions, not just in terms of size or brightness, but in terms of environment, density and emptiness, interaction and isolation, and all of these extremes exist simultaneously. Now there's another subtle point. Even in isolation, a galaxy is not completely disconnected. Gravity still acts. Dark matter still shapes its structure. Stars still evolve. So while it may be alone in a local sense, it is still part of the larger universe, still influenced by the same fundamental laws, still moving, still changing, just more slowly, more quietly. And that quietness becomes part of its identity. Once you begin to feel comfortable with the idea of a single galaxy, even one that stretches across hundreds of thousands of light years, there comes a moment where that sense of scale shifts again. Not abruptly, but in a way that gently pulls your perspective outward. Because galaxies, no matter how large or unusual, are rarely alone. They gather. They move together under gravity. And when enough of them come together, something larger begins to take shape. Not just a collection, but a system. A structure where individual galaxies become components of something far more extensive. These are galaxy clusters. and they represent one of the first steps where the scale of the universe begins to move beyond individual objects and into something more interconnected. To ease into this idea, it helps to start with something familiar. The Milky Way, for example, is not isolated. It belongs to a small group of galaxies known as the local group. This group contains a few dozen galaxies, including the Andromeda Galaxy, and several smaller companions. That might sound like a cluster at first, but it's actually on the smaller side. A galaxy cluster is something much larger. Instead of dozens of galaxies, it can contain hundreds, sometimes thousands. Instead of spanning a few million light years, it can stretch across tens of millions. And within that space, gravity weaves everything together. One of the most well-known examples is the Virgo cluster. This cluster lies relatively close to us in cosmic terms and contains more than 1,000 galaxies. At its centre sits a dominant galaxy, Messier 87, which we've already encountered as home to one of the most massive known black holes. But the Virgo cluster is not just a collection of galaxies surrounding a central point. It is filled with something else as well: hot, diffuse gas. This gas is so hot that it emits X-rays, invisible to our eyes but detectable with specialized instruments. In fact, a significant portion of the cluster's ordinary matter exists not in stars, but in this intergalactic gas. And that detail shifts the picture again, because when you think of a cluster, it's easy to imagine galaxies as the main components. But in reality, much of the mass is spread out between them, and beyond that, as we've seen before, there is dark matter, forming a much larger invisible structure that holds everything together. So a galaxy cluster is not just galaxies, it's galaxies, gas, and dark matter, all interacting within the same gravitational system. Another striking example is the Coma cluster. This cluster is even richer than Virgo, containing thousands of galaxies packed into a relatively dense region of space. If you were to observe it from a distance, it would appear as a dense cloud of light, with individual galaxies blending into a larger glow. Within the Coma cluster, galaxies move at high speeds, influenced by the combined gravitational pull of the entire system. And those motions tell us something important. They reveal that the visible matter alone is not enough to hold the cluster together. Just like with individual galaxies, the presence of dark matter becomes essential. Without it, the galaxies would move too quickly and escape the cluster's gravitational pull. So once again, something unseen defines the structure. But perhaps one of the most famous and revealing examples is the Bullet cluster. The Bullet cluster is actually the result of two galaxy clusters colliding. Not a quick collision, but a slow, massive interaction, similar to what we discussed with individual galaxies, but on a much larger scale. What makes this system particularly important is what it shows about dark matter. When the two clusters passed through each other, the galaxies continued moving with relatively little direct interaction, since the distances between stars are so large. The hot gas, however, did interact. It slowed down, compressed, and heated up, creating a bright X-ray signal. But the most interesting part came from mapping the overall mass of the system using gravitational lensing. That mapping revealed that most of the mass was not located where the gas was. Instead, it was aligned with the galaxies, which had passed through each other more freely. This provided strong evidence that dark matter behaves differently from ordinary matter. It does not interact in the same way. It passes through collisions more easily, remaining associated with the galaxies rather than the gas. So the Bullet cluster became one of the clearest pieces of evidence that dark matter is not just a theoretical concept, but a real component of the universe with distinct properties. As you sit here, perhaps noticing how your sense of scale has shifted once again, there's something almost steady about this progression. We started with individual stars, then galaxies, now clusters of galaxies, each step expanding the picture, each step revealing new layers of structure, and yet the same principles continue to apply. Gravity pulls things together, energy flows, matter organizes itself over time. Now, Consider the size of these clusters. If a galaxy like the Milky Way is already difficult to imagine in full, a cluster like Coma pushes that difficulty even further. Thousands of galaxies, each containing billions of stars, all moving within a shared gravitational field. And beyond that, a vast halo of dark matter extending even further. At this point, the word large has long since lost its usefulness. We are dealing with structures that exist on scales, where comparison becomes almost abstract. But even here, there is still structure. Clusters are not random collections, they have centers, densities, patterns of motion. They evolve over time, merging with other clusters, growing larger, becoming part of even bigger systems. And that leads to another step, because galaxy clusters themselves are not the largest structures in the universe, they are part of something bigger. Superclusters, and beyond that, the cosmic web. But before we move further into that scale, it's worth pausing here for a moment, because galaxy clusters represent a kind of threshold, a point where individual galaxies stop being the main focus, and the relationships between them become more important. Interactions, distributions, large-scale dynamics, all of these begin to define the system, and within these clusters, many of the extremes we've discussed find a place. Giant galaxies at the centre, starburst activity triggered by interactions, black holes influencing their surroundings, everything connected, everything part of the same larger structure. As your thoughts continue to slow, becoming a little more open to the vastness of it all, it becomes easier to accept that scale in the universe is not fixed. It expands, layer by layer, each one building on the last. Silence, in everyday life, is never absolute. Even in the quietest room there are small sounds, air-moving distant echoes, the faint presence of something happening just beyond your awareness. Stillness, when you notice it, is usually layered with subtle activity. But on the larger scales of the universe, there are places where that sense of quiet becomes something deeper. Not just an absence of sound, because space itself doesn't carry sound in the way air does, but an absence of activity. Regions where very little changes, where temperatures drop toward the lowest values physically possible, where matter is so sparse that interactions become rare. These are the coldest and quietest corners of the cosmos, and they represent a different kind of extreme, not defined by energy or brightness or motion, but by stillness. To ease into this idea, it helps to think about temperature. Temperature, at its most basic level, is a measure of motion. The faster particles move, the hotter something is. The slower they move, the colder it becomes. At absolute zero, the theoretical lowest temperature, motion would effectively stop. In practice, nothing in the universe reaches absolute zero, but some regions come remarkably close. One of the most pervasive examples is the cosmic microwave background. This is not a galaxy, but a faint glow that fills the entire universe, a remnant of the early stages after the Big Bang. It has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. Every galaxy, every cluster, every void exists within this background, so even the emptiest regions of space are not completely empty. They carry this faint uniform temperature. But within that baseline, there are places that feel even quieter. Cosmic voids, which we touched on earlier, are among the best examples. These vast regions contain very few galaxies, very little gas, and very low densities of matter overall. With fewer stars, there is less radiation, less heating, and fewer interactions to stir things up. In these regions, temperatures can drop closer to that cosmic background level. And because matter is so sparse, processes that rely on interaction, like star formation, become extremely rare. One particularly striking example is the Buta's void. The name might sound unfamiliar, but its scale is difficult to ignore. The Buta's void is one of the largest known voids in the observable universe, spanning roughly 330 million light-years across. Within that immense volume, there are surprisingly few galaxies. If you were to travel through this region, not that such a journey is possible in any practical sense, you would spend vast stretches of time without encountering anything at all. No nearby galaxies, no clusters, just long extended distances between the few structures that do exist, and within those distances the environment remains cold, not in a way that you would feel, but in the sense that there is very little energy being exchanged. Particles move slowly, radiation is minimal, interactions are rare. There's also another example that feels even more specific, the Boomerang Nebula. While not a galaxy or a void, it is one of the coldest known natural objects in the universe, with temperatures measured at around 1 Kelvin. That's even colder than the cosmic microwave background. It achieves this through a rapid expansion of gas, which cools as it spreads out. In a way, it shows that under the right conditions, regions can become colder than the general background of the universe. Now, when we bring this back to galaxies, the idea of cold and quiet often relates to how much activity is taking place. Galaxies in dense clusters are surrounded by hot gas, interacting with their environment, influenced by nearby structures. Galaxies in more isolated regions, especially within or near voids, experience something different. Less interaction, less disturbance, a slower pace of change. These galaxies may continue forming stars, but often at a reduced rate. Their gas is not being compressed by collisions or interactions, so the processes that trigger intense star formation are less common. Over time, they can settle into a quieter state, not completely inactive, but less dynamic. And that quietness extends beyond individual galaxies. It becomes a property of the region itself. As you sit here, perhaps noticing how the tone of this section has become a little softer, a little more still, there's something fitting about that. Because these regions are not meant to be dramatic. They are not the places where the universe announces itself with brightness or motion. They are the spaces in between, the areas where things simply exist. And that existence is important, because without these quiet regions, the contrast we've been exploring wouldn't exist. The brightest galaxies stand out because there are darker regions. The most active systems feel intense because there are places where almost nothing happens. So the extremes are connected. Activity and stillness, heat and cold, density and emptiness. Each one defines the other. There's also a long-term perspective to consider. As the universe continues to expand, these voids are expected to grow. Galaxies within them will move further apart. Interactions will become even rarer, and over extremely long timescales, much longer than the current age of the universe, these regions may become even quieter, even colder in a relative sense. In that future, the universe may feel less connected, more isolated, structures drifting further from one another, with vast stretches of space in between. And that brings a different kind of stillness. Not just a snapshot of quiet, but a gradual trend toward it. Now consider how this connects to everything we've explored so far. Galaxies that burn intensely, galaxies that collide and merge, galaxies that shine with extraordinary brightness. And now regions where very little happens at all. Each one represents a different way in which matter and energy can be arranged, different outcomes from the same underlying laws. As your thoughts continue to slow, becoming a little more open and less focused on individual details, it becomes easier to accept that the universe is not defined by a single state. It contains extremes in every direction, not just in size or speed, but in activity. From the most energetic systems to the quietest corners, everything exists within the same vast structure. After exploring the quietest regions, the next question is not just about what exists now, but what will exist in the future. Time, when you stretch it far enough, begins to feel less like a sequence of moments, and more like a slow unfolding. Not something that rushes forward, but something that gradually reshapes everything it touches. And when we begin to think about galaxies in that way, not just as they are now, but as they will become, the perspective shifts again. Because galaxies are not fixed structures. They are temporary arrangements, stable for billions of years, yes, but still evolving, still changing, still moving towards something else. To ease into this, it helps to start with something familiar. The Milky Way feels permanent. Its stars move in steady orbits, its structure holds together, and on human timescales, nothing about it seems to change in any noticeable way. But given enough time, even something as large and stable as the Milky Way will transform. We've already touched on one part of that future, the slow approach of the Andromeda Galaxy. Right now, it's a distant presence in the sky, a faint smudge of light visible under dark conditions. But over the next few billion years, gravity will draw the two galaxies closer together. Their structures will begin to distort. Their gas will compress. Waves of star formation will ripple through both systems, and eventually, after a long, gradual interaction, they will merge. Not in a sudden event, but through a series of passes, each one bringing them closer to a final unified structure. The result will likely be a large elliptical galaxy, something different from either of the original spirals, and that's one of the key ideas when thinking about the future of galaxies. Mergers change everything. Spiral galaxies can become elliptical, structures can be reshaped, mass can be redistributed, but that's only part of the story, because not all galaxies will merge, some will drift apart, and that difference comes from something we've mentioned quietly in the background throughout this journey, the expansion of the universe. Since the Big Bang, space itself has been expanding. Galaxies that are not gravitationally bound to each other are moving apart, carried by that expansion. On smaller scales, within clusters or groups, gravity can overcome this expansion, keeping galaxies together. But on larger scales, the expansion dominates, and over time, that effect becomes more pronounced. Galaxies outside our local group will continue to move further away. Their light will become more redshifted, stretched to longer wavelengths. Eventually, they will move beyond the point where their light can reach us at all. Not because they have disappeared, but because the space between us and them is expanding too quickly. So in the very distant future, the observable universe will look very different. From our perspective, most galaxies will no longer be visible. Only those gravitationally bound to us will remain within view. Everything else will fade beyond the horizon. As you sit here, perhaps noticing how this idea feels a little more expansive, a little more abstract, there's something quietly profound about that. Because it means that what we see now is temporary, a snapshot, a moment in a much longer process. Now, consider what happens within galaxies themselves. Star formation, as we've seen, depends on gas. Cold, dense gas that can collapse under gravity. But that gas is not infinite. Over time, galaxies use it up. Stars form, evolve, and eventually die, returning some material back to the interstellar medium, but not always in a form that can easily form new stars again. So as time goes on, the rate of star formation declines. Galaxies become quieter. Older stars dominate. Redder light replaces the bright blue glow of young massive stars. In a sense, galaxies age. Not in a biological way, but in a gradual shift of activity. From active, star-forming systems to more passive, stable ones. We've already seen examples of this in galaxies like Messier 87, where star formation has largely stopped. In the future, more galaxies will move toward that state. Not all at once, not uniformly, but as a general trend. Less gas, fewer new stars, more long-lived, stable systems. There's also the role of black holes to consider. At the centres of many galaxies, supermassive black holes continue to exist, sometimes active, sometimes quiet. Over time, as galaxies merge, these black holes can merge as well, growing larger. Their influence can continue to shape the surrounding galaxy, heating gas, preventing new star formation, maintaining that quiet state. So even in the absence of dramatic events, there is a kind of slow evolution taking place. Now, if we extend this timeline even further, far beyond the current age of the universe, the picture becomes even more still. Stars themselves have lifetimes. Massive stars burn out quickly, in millions of years. Smaller stars like the Sun last for billions. The smallest stars can last for trillions of years, but eventually even those will exhaust their fuel. They will fade into remnants, white dwarfs, neutron stars, black holes. And over extremely long timescales, galaxies will no longer contain bright shining stars. They will become collections of remnants, orbiting quietly in the dark. This is sometimes referred to as the degenerate era of the universe, a time when the processes that produce light have largely ended. But even before reaching that distant future, there is a more immediate shift to consider. The universe is not just expanding, it is accelerating in its expansion, driven by something we call dark energy. This means that over time, the separation between unbound structures increases more rapidly. Clusters become more isolated from each other. Voids grow larger. The overall structure of the universe becomes more spread out. So the future of galaxies is not just about internal changes, it's about their relationships to one another. Closer systems merge, distant systems drift apart, and the balance between these processes shapes what remains. As your thoughts continue to slow, becoming less focused on precise timelines and more open to the broader picture, it becomes easier to see how this all connects. Galaxies are not permanent, they are phases, stages in a longer process of cosmic evolution. They form, grow, interact, and eventually settle into quieter states. And beyond that, even those states change. There's something almost gentle about that idea. Not in the sense that it's simple, but in the sense that everything unfolds gradually. No sudden ending, no abrupt transition, just a continuous shift from one state to another. Now, consider what that means for everything we've explored so far. The largest galaxies, the brightest quasars, the fastest rotations, the most intense starbursts. All of these are temporary conditions, moments in the life of a galaxy. Given enough time, they change, they fade, they evolve into something else, and that perspective changes how you think about extremes. They are not fixed categories, they are points along a timeline, different expressions of the same underlying processes. Patterns can feel convincing, especially when you've seen them repeat enough times. A spiral galaxy here, another one there, a quiet rhythm of star formation, a general sense that, while the universe is vast and varied, there are still underlying rules that most things tend to follow. And for a while, that's exactly how galaxies were understood. There were categories, spirals, ellipticals, irregulars, each with its own typical behaviour, its own expected structure. Some variation, of course, but still a framework that felt stable enough to rely on. Then the outliers began to appear. Galaxies that were too large, too bright, too faint, too fast, too early. At first they seemed like exceptions, rare cases, interesting but not representative. But as observations improved, as telescopes like the James Webb Space Telescope began to look deeper into space and further back in time, something subtle started to change. The number of these exceptions began to grow, and when enough exceptions appear, the question naturally shifts. Are they really exceptions at all? Or are they part of a larger pattern we haven't fully recognised yet? To ease into this, it helps to think about how we observe the universe. We don't see everything equally. Bright objects are easier to detect than faint ones. Large structures stand out more than small ones. Active systems, those producing a lot of energy, are more noticeable than quiet, stable ones. So from the very beginning, our view of the universe is shaped by what stands out, by what is easiest to observe, and that introduces a subtle bias. We are more likely to notice extremes, the brightest quasars, the largest galaxies, the most intense starbursts, not necessarily because they are the most common, but because they are the most visible. But as technology improves, that picture becomes more balanced, fainter galaxies become detectable, more distant systems come into view, and with that expanded perspective, the distribution of galaxy types begins to look more complex, more continuous, less neatly divided into normal and extreme. Because what we often call extreme is simply a position on a spectrum. Take star formation, for example. Some galaxies form stars slowly, others form them rapidly. There isn't a sharp boundary where one category ends and another begins. There's a range, a smooth transition from low activity to high activity. The same applies to size. There are small galaxies, large galaxies, and everything in between. Even the most massive systems are not isolated points, but part of a broader distribution. As you sit here, perhaps noticing how these ideas are becoming a little more connected, there's something quietly reassuring about that. Because it suggests that the universe is not divided into strict categories. It's continuous, flexible, capable of producing a wide range of outcomes under the same underlying laws. Now consider the early universe. When astronomers look back to the first billion years after the Big Bang, they don't just see a few unusual galaxies, they see many systems that appear more developed than expected, more massive, more active, more structured. At first, each of these discoveries felt surprising, but as more data comes in, a different possibility emerges. Maybe the early universe was simply more extreme, denser conditions, more frequent interactions, faster processes. What seems unusual from our current perspective might have been more common back then, and that shifts the idea of what normal means, because normal is not fixed. It depends on context, on time, on environment. A galaxy that looks extreme today might have been typical in a different era. Now think about galaxy clusters. In dense environments like the Coma cluster, interactions between galaxies are frequent. Collisions, mergers, gravitational influences, all happening over long timescales. In such regions, unusual structures, disturbed shapes, intense star formation become more likely. So what might be rare in isolation becomes common in a cluster. Again, context matters. And that idea extends even further. Because the universe itself is not uniform, it contains regions of high density and low density, clusters and voids, active environments and quiet ones. Each region supports different kinds of galaxies, different evolutionary paths. So when we ask whether extremes are the rule or the exception, the answer becomes more nuanced. In some places, extremes are common. In others, they are rare. There is no single universal baseline. There are multiple baselines depending on where and when you look. There's also something else to consider, our definitions. What we call extreme is based on our current understanding, on the models we've built, the expectations we've formed. But as those models evolve, as new observations come in, the boundaries of what counts as extreme can shift. A galaxy that once seemed impossible becomes explainable. A rare phenomenon becomes part of a known category. So the concept of extreme is not fixed either. It changes as our knowledge grows. As your thoughts continue to slow, becoming less tied to rigid categories and more open to this broader perspective, it becomes easier to accept that the universe doesn't organize itself around our expectations. It doesn't aim to be typical or exceptional. It simply allows for possibilities, and those possibilities span a wide range. Now, consider how this connects to everything we've explored so far. Galaxies that form too quickly, galaxies that stop forming stars, galaxies dominated by dark matter, galaxies that lack it, galaxies that shine intensely, galaxies that are barely visible. Each one represents a different point in a multidimensional space of possibilities. Not isolated anomalies, but part of a larger continuum. And when you step back far enough, that continuum begins to feel more natural, less surprising, more like an inherent property of the universe, variation, diversity, a range of outcomes emerging from the same fundamental laws. There's something quietly calming about that, because it means that nothing we've seen is truly out of place. Even the most unusual galaxies fit somewhere within the broader pattern. They might be rare, but they are not impossible. They might be surprising, but they are not disconnected. Everything belongs. Everything has a place. By now, the scale of everything we've explored has had time to settle a little. Not fully, perhaps, because the mind doesn't quite hold on to numbers like billions of light years or trillions of stars in a precise way. Instead, those ideas soften at the edges, becoming more like impressions than exact figures, and that's perfectly fine. Because this wasn't really about measuring the universe in strict terms. It was about drifting through it, slowly, letting each piece appear, linger for a moment, and then gently give way to the next. We started with galaxies that felt familiar, the kind that resemble our own Milky Way, with their quiet spiral arms and steady motion. From there, the scale widened. Larger galaxies, brighter ones, stranger ones, each pushing against what we thought was typical. Some grew too fast, some barely formed stars at all. Some shone so intensely that they outshined entire systems, others faded into near invisibility, spread thin across space like faint outlines. And somewhere along the way, the idea of normal began to shift. Not because the rules changed, but because the range of possibilities became clearer. Galaxies weren't just one thing. They were many things, different outcomes shaped by the same underlying forces. Gravity pulling matter together, energy flowing through stars, time stretching everything out across billions of years. And as those processes unfolded, they created structures that range from the intensely active to the almost completely still. From crowded clusters to vast empty voids. From galaxies dominated by visible stars to those held together mostly by something we can't see. All part of the same universe, all existing at the same time. As you sit here perhaps feeling a little more settled than when this began, there's something quietly grounding about that. Because even though the scale is enormous, even though the distances are almost impossible to picture, the underlying ideas are simple. Things come together, they change, they move, they evolve, and over time, they become something else. Now, there's another way to look at all of this. Instead of focusing on how large or extreme these galaxies are, you can think about how long their stories have been unfolding. The light we see from distant galaxies left them billions of years ago. Some of those galaxies have already changed, some may no longer exist in the form we observe. What we're seeing is not a single moment, but a collection of moments, each one captured at a different point in time. It's almost like looking at a timeline spread across the sky. Every direction you look, every galaxy you observe, represents a different part of that timeline. And by piecing those observations together, we begin to understand how the universe has evolved. Not all at once, but gradually, step by step. There's something calm about that kind of perspective, because it removes the need to hold everything in your mind at the same time. You don't need to grasp the entire universe. You just follow one thread, then another, and slowly a picture forms. Now, consider how that connects back to where you are. Right now, in this moment, wherever you happen to be listening, the room around you, the quiet sounds in the background, the steady rhythm of your breathing, all of that exists on a completely different scale, and yet it's part of the same system. The same physical laws that shape galaxies also shape everything around you. Gravity, energy, motion, time. They don't change just because the scale does. They remain consistent, whether you're looking at something the size of a room or something the size of a galaxy cluster. And that consistency is what makes the universe feel connected, even when the distances are vast, even when the structures are extreme. There's a continuity that runs through everything. As your thoughts continue to slow, becoming less focused on specific details and more open to the overall feeling of it all, you might notice something else. The extremes we've explored, the largest galaxies, the brightest quasars, the fastest rotations, they don't feel as overwhelming anymore. Not because they've become smaller, but because you've had time to adjust, to move through them at a steady pace, to let each idea settle before moving on. And in doing so, the vastness becomes something you can sit with, rather than something you need to fully understand. Now there's one last gentle shift to make. Instead of looking outward, across billions of light years, you can let your attention come back inward. back to the present moment, back to where you are. Because while the universe continues its slow, steady evolution, while galaxies merge, form stars and drift apart, none of that requires anything from you right now. There's nothing to solve, nothing to hold on to. The universe will continue whether you think about it or not, and that can be a comforting thought. Because it means you don't have to carry it. You can simply observe, or even let it fade into the background. The same way the night sky fades as you close your eyes. If your mind is still a little active, that's okay. Thoughts tend to linger for a while. They move at their own pace. But just like everything else we've explored, they can slow down over time. They can become quieter, less urgent, more like distant signals than immediate concerns, and eventually they can drift. Now, imagine for a moment that you're looking up at the night sky, not focusing on any particular star, not trying to identify constellations, just letting your gaze rest on the darkness itself. There's a kind of softness there, a sense that the vastness doesn't need to be filled. It can simply be, and in that space there's room to let go of the details, to stop following each thought all the way through, to let them pass the way galaxies drift through space slowly, without urgency. As that happens, your awareness can settle, your breathing can remain steady, your body can relax a little more, and the ideas we've explored, all those galaxies, all those extremes, can begin to feel more distant, not gone, just further away, like light that left its source long ago, still travelling, but no longer needing your attention. There's no need to reach the end of anything here, no need to conclude or summarise in a final way, just a gentle continuation, a slow fading of focus. Because even as this narration comes to a natural pause, the universe itself continues quietly, steadily, without interruption, and you can rest within that, letting the vastness remain vast, letting the details soften, letting everything move at its own pace, and as your thoughts drift further, becoming lighter, less defined, you might find that the sense of scale we've explored doesn't feel overwhelming anymore. It feels calm, open, almost still, and from there, without needing to force it, you can simply continue resting in that quiet space.